These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay. So what is the domain of f of x?
Okay.
Based on this graph.
Okay. It is 3 through 7.
Okay, great. Now, what's a good notation for that? A good notation for that would be like this, to show that that's the interval. Okay, so it looks like you've already learned this concept of domain. So what is the domain of the function? The domain of the function are the inputs for which the function is defined. The domain of the function are the values of x for which the function is defined, or the values of the input variable for which the function is defined. So the domain of this function would be 3, 7. Okay, good.
Cool.
This is then what's called a closed interval because it includes 3 and 7. Suppose that the domain did not include 3 and 7. Well then, we would write the function like this. When you use an open circle, that means that the points on the end are not included. Do you know how you would write the domain here?
I think I would write it still as 3 and 7, but with, instead of brackets, I would just use I think just parentheses.
That's right, yep.
Okay.
So this is what's called an open interval. So does an open interval include the endpoints?
It does not.
No, it doesn't. So this is the notation for an open interval, and this is how you graph an open interval. On the other hand, this is how you would graph a closed interval, and this is how you would notate it. So does a closed interval include the endpoints?
Yep.
Yeah. And that's what we're really focusing on in this chapter. Almost all the problems are about closed intervals, so we'll be focusing on that. Okay, very good. Is this function continuous?
It is.
Yeah, this function is continuous. Is this function continuous?
No, jump discontinuity.
It's discontinuous. Yes, it has a discontinuity. Good.
Okay.
So the technical definition of continuity is pretty complicated and confusing, but intuitively you kind of know it when you see it, right? So a function is continuous if you can trace it with your pencil without lifting up your pencil. A function is continuous if you can trace it with your pencil without having to lift your pencil up off of the page. Well, this is discontinuous because if I was tracing this with my pencil, when I got to here, now I have to lift my pencil off the page and move it and then set it down over here. So it's discontinuous. Okay, good. Whoops. Is this function continuous or discontinuous?
That function is continuous.
Because you could trace it with your pencil all the way through without ever having to pick your pencil up off of the page. Okay, so the intuitive definition of a continuous function is one that you could trace without lifting up your pencil. That's pretty easy to identify when you see it. Okay, tell me when you have these written down.
Mm-hmm. Yep.
Okay, good. All right, so these are the definitions of absolute and local maximum. Now, again, obviously these are not technical definitions, but these are intuitive definitions that should allow us to get the problems correct. Okay, so, and it should be pretty obvious how you could write down definitions for absolute minimum or local minimum based on these. So, here's an example of a function, f of x. So according to our definitions, we would say that this point is a local maximum. Do you see how this would be considered a local max?
Right, because it's above the peak, well, the valley to the right.
And the left.
And the left, okay.
So the point is, it's greater than the points to its left and to its right. A local max is greater than the points to its left and its right. Now, wait a second. It's not greater than this point, but that's okay because it only has to be greater than the local points. It doesn't have to be greater than all the points.
Okay.
And again, for your course, we don't need to worry about getting a full technical definition of what it means to be a local maximum. We just want to get to the point where we know it when we see it, if you see what I'm saying. Mm-hmm. So this kind of looks like a local max, hopefully. So what term could we apply to this point?
That's the local min.
Is it a global min?
It's not.
No, because there's other points that are lower, like this point. So what term could we apply here?
That's the absolute max.
Great. Because it's greater than all the points. But also, would you agree, if you wanted to, you could also call it a local max?
Yeah.
Because it's also greater than the local points to its left. It's also greater than the local points to its left and to its right. That seems a little bit pointless because it's much more exciting to say that it's an absolute max. But if we wanted to be nerdy, we could also say it's a local max. Okay, good. What would be a good term for this point?
That's a local min.
Is it a global min?
It's not.
No, because there's other points that are lower, like this. What could we call this?
That is a local max.
Very good. Okay. Now, how about this point here?
That is just an endpoint, so it can't be a local min or an absolute min. It's just a point.
Okay, we'll have to clarify that a little bit. This
Okay.
is the absolute min. Because all it takes to be absolute maximum or minimum is to be, all it takes to be the absolute minimum would be to be less or equal than all the other values of the function. And this that point there really is less than all the other points. So this is the absolute minimum. Okay. However, and here's what I think you were probably thinking about, according to the definition used in your textbook, it is not a local minimum.
Okay, that makes sense.
To me, that seems a little bit weird. To me, this definition seems a little bit weird, but this is the definition your textbook uses, so we just have to get used to it. So the definition your textbook uses is what I've written down here. Notice the key thing is, according to your textbook's approach, a local minimum has to be less than or equal to all the values in a local neighborhood to the left and the right of the point. That's just the definition your book uses. But there are no points to the right of this point. So it can't be less than the points to the right of itself because those points don't exist. So if you're a stickler about the exact definition, it doesn't meet that definition of a local minimum. To me, this seems like a little bit of a weird definition, but anyway, we just have to get used to how your book does it. Okay, so that's why I was underlining this words left and right. This is the key. You have to be, a local minimum has to be less than the points to its left and to its right. So if there are no points to its right, it can't be a local minimum. And if there's no points to its left, it can't be a local minimum based on the definition your book is using. Okay. Mm-hmm. And even though that definition seems a little bit weird, it does have some advantages as well. Okay, so anyway, this is an absolute min, but not a local min. Let's go back to here. How would we classify this point?
Okay. Well, it can't be a local max, but it's also not tricky. That.
Yeah, so, I'm sorry, this one is tricky, just to warn you, but what do you think?
Okay. So it's not the absolute max. Definitely not the absolute max, and I don't think it's a local max. So I would just say it's a point.
Okay, excellent. Yeah, it was tricky, but there's just no special term for it. So first of all, I'm not quite sure why you were thinking of max, because it's not higher than other points. So what we should have been considering is whether it's a type of minimum, right? Mm-hmm. Now, it's certainly not an absolute minimum. I'll cross that out. It's definitely not an absolute minimum. And according to your book's definition, it's not even a local minimum. Because a local minimum has to be less than the points to its left and to its right. But this point doesn't have any points to its left. So using that technical definition, it can't be a local minimum either. Okay, so basically your thought process was correct. So not every point meets one of these terms. After all, this point doesn't meet any of the terms, right? It's not an absolute max, it's not a local max, it's not an absolute min, it's not a local min. Like you said, it's just an ordinary point with no special name. Well, it turns out that sometimes the endpoints are just ordinary points with no special name too. Sometimes the endpoints are just ordinary points with no special name. By the way, so what I was implying here is that this is the end of the domain. These 2 points are the end of the domain. The function is not defined outside of those points. It's defined over that interval. These are the kinds of pictures we'll be using in today's session. So if we assume that it's not defined to the left of this point, this can't be a local minimum because it can't be smaller than the points to its left because there are no points to its left. Okay. Anyway, do you have that copied down? Yep. All right. Okay, so you probably had already started to learn those terms, but there were a couple things I think we weren't quite clear about, especially I think before you might have been thinking that endpoints could never be either absolute or local mins or maxes, but now we see that's not right. Can an endpoint be an absolute minimum?
It cannot. Wait, yes, it can.
Like this one.
Right.
Okay, yeah. Good. So yeah, this is a little tricky. So I'll just repeat that question. Can an endpoint be an absolute minimum?
It can.
Yeah. Can an endpoint be an absolute maximum?
It can.
Yeah. Not in this picture, but it could.
Right.
Could an endpoint be a local minimum or maximum?
Never.
No. So that's the result of this kind of weird definition. Because local maximums and minimums have to be compared to a local neighborhood to their left and their right. So, but an endpoint doesn't have a local neighborhood to its left, or maybe to its right. So it can't ever match this definition that your book uses. On the other hand, notice that this definition of absolute maximums or minimums didn't say anything about left or right. So it's not vulnerable to that. Okay, so I think we have that, so I'll just repeat that. Can an endpoint be an absolute minimum or maximum?
Yep.
Yeah. Can an endpoint be a local minimum or maximum?
No.
No. All right, good. If you keep that in mind, these problems should make some sense. Okay, so what term would we apply here?
That's the absolute min.
How about here?
That is the local max. The local maximum. That is the local minimum. Wait, that's the local minimum. That's a local min and the local min and the absolute. Sorry, the local maximum and the absolute maximum.
Okay, that's good that you took your time and worked that out. The most reasonable thing to say here is that this is the absolute maximum, but technically it's also a local maximum because it's bigger than the points to its left and to its right. Okay?
And the last point is just a local min.
Excuse me, how about here?
That is just the end of the domain.
So nothing special.
Right.
You could call it an endpoint, that's right, but it doesn't match any of those particular terms we were talking about before. Okay, so notice that absolute maximums and minimums can sometimes be local maximums and minimums, but they don't have to be. Here we have an absolute minimum that's not a local maximum or a local minimum. Okay, good. Okay, what could we say about this point?
That is just a point.
And this point?
That is the absolute maximum and also a local maximum. That is a local min. That's a local maximum. A local minimum. A local max. The absolute min and also a local min. And that is just a point.
Yeah, nothing special. Okay, good. So that's some good progress on that technique. So let's continue. Good. By the way, why do we care where the minimums and maximums of functions are? Why is that interesting? Well, remember that one of the main purposes of math is to model things in real life. For example, what could the function stand for? The function could tell you the cost, the average cost of producing a certain level of output for a firm. Well, obviously that firm would like to find where it can minimize its costs, right? Mm-hmm. So if they've discovered a function for their average costs, they could use calculus or math perhaps to try to figure out where those average costs are minimized. Or maybe another function, maybe the function actually represents the firm's profit and X represents the price that they set. And obviously when a firm changes its price, that can change its profit. Well, obviously the firm would like to find the maximum of that function where its profit is going to be maximized. So, for example, in economics, there's lots of different applications of these types of ideas, or in general. So, in general, the maximums and minimums of a function are generally going to be very interesting to us. Very often, a person or a firm is going to want to try to go to the point on the function where their costs are minimized, or whether their profits are maximized, or where their fun is maximized, or where their boredom is minimized, or whatever. Okay, good. For example, something that the government might try to do is they might try to figure out what's the correct level, for example, let's see, what's the example that I'm trying to think of. Okay. They might be trying to, for example, set the speed limit in certain ways. So they say minimize deaths, to give you trying to think of an example from outside of economics. So for example, F might be the number of deaths, and X might be the speed limit. So they might want to be minimizing, hopefully, the number of deaths. So there would be kind of a trade-off here, because when you lower the speed limit, there's fewer deaths on the road. There's fewer deaths on the road, but people have to spend more time on the road, for example. That example was terrible. All right, so I'm having trouble thinking of good examples, but trust me, there's lots of examples where people want to maximize or minimize functions.
Yeah, the stuff with the firm makes sense. I've taken a few of those classes before, and they're quite interesting, I think. So
good, excellent. I didn't want to give you the sense that this only applies to economics, but that happens to be all I could think of off the top of my head. But in your textbook, there's tons of other examples. Okay, so anyway, moving on, let's see how this comes up now. Okay, so let's say we have a function that has a absolute max at 3, absolute min at 2, local max at 3 and 5, local min at 4, and the domain is 2 to 6.
Okay.
All right, tell me when you have that written down.
Yep.
Okay, so I'll just show you what I think is the best process for this type of problem. So we have our domain here. So we know the domain is going to be going from 2 to 6. So I think the best way to attack this type of problem is first organize the information from smallest input to largest input. So I would rearrange this as two is the left endpoint, and it's an absolute minimum. And then the next number I see here is 3. 3 is an absolute max. And then reading along, I notice it's also a local max. And that's all they said about 3. So then I would look for the information they have about 4. And they said 4 is a local min. And then I would look for the next point. Well, next they mentioned 5. So the point is put the information in order. And they said that was a local max. And then next thing they said was 6, but all they said about 6 is that it was the right endpoint. So this is a good technique for attacking this type of problem, although I wasn't very organized about it. So here's, the point is reorganize the information. So then we could start here at x equals 2. This is a closed interval, so I put a dot here. Now I know that 3 is a maximum. So this portion of the graph must look like this. That's the only way that 3 could be a maximum, absolute and local. So far, so good? All right, then 4 is a local minimum. So I know that at 4, we're going to turn around like this. And maybe I should make a note here. I wanted this to be the absolute max and a local max, and this is supposed to be a local minimum at 4. Then 5, they said, is going to be a local max. So notice I have to be careful. Do you see how I couldn't draw it like this?
Right.
Why would this mess up?
Because now when x is 5, you'd have an absolute max, but that's not what the problem tells you.
Yeah, that would be bigger than over here. So I should have given myself more space. But I have to have it turn around like this so that it can be a local max, but so it's still beneath this absolute max. All right, and then just moving on down, we're going to go... Oh, I forgot to mention, I didn't label 2 was supposed to be the absolute minimum. I got sloppy here. So that's one reason why I have to make sure all the other points never drop below this point here. So then 6 is going to be the end point, but I can't make 6 look like this, because then it would go below the absolute minimum. So I have to be careful to go down it kind of shallowly and end up over here. And then there's nothing special about 6 terminologically wise, but it's going to be above 0.2. Notice that to make your graph work out, it's helpful to make these kind of dashed lines so that, that the reader can see. This way the grader knows you know what you're doing. And so they can see that you're putting everything in the right point. It's probably a good idea when you're done to go back and double check everything. So let's see, absolute max at 3, yes. Absolute min at 2, yes. Local max at 3, yes. 5, yes. Local min at 4, yes. We could make little check marks like we were when we were doing proton spectroscopy. And we have the domain here is 2 to 6. Okay, so anyway, this is the kind of method I would suggest here. Now keep in mind, this is not the only possible answer. There's a billion possible ways you could draw this that would be consistent with this information. So I'm not saying this is the only answer, but this is a good way to come up with the answer, except that you should try to draw a bigger graph than me so you have more space, because you want it to be clear to the reader which points are above and below the other points. I shouldn't have tried to cram it in like this. The one thing here that I think is helpful is before you make the graph, rewrite all the information from small to big. Because the information isn't organized in a helpful manner here. So it's better to reorganize it like this, and then you can kind of read off what you need to do as you move along the graph. Okay, so far so good?
Yep.
All right. Good.
Absolute min. Seven is local max. And okay, 6
Good. So it's just important to
absolute.
be very careful to copy everything accurately.
Yeah. So 6 is absolute min, 7 is local max, 9 is local min, and 10 is absolute max. Okay.
Good. That's good that you're double checking. Why don't you spread out those hash marks more to give yourself more space? And if you want to, you could pretty much just graph, 6 through 10.
Oh, okay, true. Okay.
As long as you label them so that the reader knows what they are.
Okay, X, Y. All right, so 6 is the absolute minimum. So I'm going to put this low. 7 is the local max. So 7 is a local max, so it's going to be higher than 6.
Good. But it's good you didn't go too high because you still need to leave room for the absolute max. Good.
9. Okay, 8 skip. 9 is a local minimum, so I'm going to put it a little bit below 7. Oh. Maybe I should.
Looks like actually maybe we should have made 7 a little higher.
Yeah, a little bit.
And maybe we should have put our graph closer to the bottom of the screen so we had more space. When you do these on the test, you want a nice big graph so the reader can see clearly that you're getting the right answers. Now, as you're going, it would be best to label the points so that you can keep checking that you're getting them right.
Absolute min. Local max at 7. 9's a local minimum. And 10 is absolute max. Six absolute min to the local max to the local min to the absolute max. 10, 9, 7, 6. Okay.
Okay, good. Yeah. Again, if this was a test question, you'd want to have more space so it was clearer that 6 really is lower than 9. But I think we got this right. Okay, now let's plot some points on the y-axis. Put in a dashed line and make up a coordinate for the point at 6. Just make up a number that might be. 5, that's fine. Now let's make up a y-coordinate for 7 with a dashed line. Okay, good. So I just wanted to talk about then, it's important here to distinguish when you're dealing with functions between the inputs and the outputs. So for example, 6, 7, actually then it would be easier then, why don't, instead of calling those 5 and 10, why don't you call them 50 and 100 on the y-axis, just so that there's a clearer distinction between them. So that point, that coordinate of 6, does that represent an input or an output?
That's an input.
And how about the 50?
That's the output.
Right. So point to the absolute minimum. Good.
Right here.
What is the absolute minimum? 50, or 6?
The absolute minimum is 50.
But it occurs at 6.
Mm-hmm.
So we want to see the distinction between those two things. We need to be able to talk clearly about that. The absolute minimum is the minimum output. The absolute minimum and maximums, all the minimums and maximums, their values refer to the outputs, but they occur at the inputs. So it's important not to get confused about those things as we go. We don't want to confuse inputs and outputs. So if we say the absolute minimum, good. So forget about this problem for a second. If I say the absolute minimum is 16, if I say the absolute minimum is 16, am I talking about an output or an input?
You're talking about the output.
Good. But if I talk about the absolute maximum at 22, the absolute maximum at 22, is 22 an input or an output?
22 is the input.
Okay, good. All right, so it's just important to be clear about the terms that are used here to distinguish between the inputs and the outputs. Notice that for these type of graph questions, we don't even have to know what the exact outputs are. We've really just been focusing on the inputs. All we have to do is get the right shape of the graph at the right inputs. We have we don't actually have to actually label the outputs, but later on we'll have to deal with the outputs as well. Okay, good. I'm going to go back to my screen.
Okay.
Okay, let's try this one. So this is part B of the same introduction.
Max at 10, max at 8, number 7. So just draw a new graph for this one, right?
Sure.
Okay. All right, I guess I could draw on this one, but.
So let's give ourselves a whole fresh screen because we want to be able to spread out on these problems.
Okay. Okay. So. Okay. So 7, 8, 9, 10. 7 is the absolute min. 7 is the local min. 10, 8 is the local max. Nines. 10. Okay. 7 is the absolute min and a local min. So oh, there's 6 too. Okay. That's right. Okay. Six is an endpoint, and 7 is the minimum. So make 6 here. 7 is the absolute min and a local min. Okay. So I guess that's a bad place to put that. I'll make the next graph bigger. Yep. Okay. So 7's absolute min and local min. And 8 is a local max, so 8's a little bit bigger. Maybe there. And 8's a local max. And 9's a local min, but not the absolute. So here. And 10's absolute max. So 6 is the endpoint of the domain, 10 is the endpoint of the domain. 7 is the absolute min and a local min. To a local max, to a local min, the absolute max, and then of the domain. Okay, cool. I think this is good.
Okay, good. Draw a horizontal line through the point at 7. Draw a horizontal line through the point at 7.
It's a straight line.
Yeah, a dashed line.
Okay, sorry.
Because it's not actually part of the graph. It's a reference line like your vertical lines. And draw it to the left as well. That would be a good thing to do on the test because that shows the reader that it really is below all the other points.
Oh, okay,
that you've clearly made it an absolute min. Because notice one of them is a little bit close. The reader might think that you weren't quite sure and you're trying to have it both ways. So this way we can make it clear that we're stating a firm position about who the absolute min is. Of course, you got it labeled anyway. Mm-hmm. And now also draw a horizontal line through x equals 10.
Horizontal. Oh, okay.
Because that demonstrates that it really is the max. So that's just something you might do on these problems to through the max and the min to demonstrate that they really are the max and the min. In fact, you might do that even while you're solving the problem to make sure you don't accidentally go above the max or the min.
Okay. There.
Why is that so funny?
Yeah.
All right. Very good. All right, so let's see. Okay, very good. And there's more of these that you can practice in the textbook, so I'll let you practice this more in the textbook. With practice, we can get better at managing our space. Notice that there's tons of space above and below the graph that we could have used here, and that would make the graph clearer. So with practice, you get better at managing the space so that the points are not so close to each other. By the way, of course, there's no rule that says they all have to be above the x-axis. Some of them could be negative, but why bother? It's probably simplest just to put them all in the positive quadrant. So for these problems, you might as well keep doing what we've been doing here and put them all in the positive quadrant just to make it easier. Okay, so it would be a good idea to practice that some more, but I think we have the basic idea, so let's keep moving on. So I'm going to go back to my screen.
Okay.
Like I said, there's a few more in the textbook that you can practice like that.
Mm-hmm.
Okay, so now let's talk a little bit about where we are here in the course. One thing we've seen in this course is one of the things that you need to do well in this course is you have to learn calculus, obviously. However, we've also seen that sometimes we need to go back and refresh our high school algebra as well, or maybe also our high school trigonometry. And that's actually going to be especially important here. I think the material in this chapter, the calculus, is pretty easy. You've already done the main calculus in the previous chapter when you learned how to take derivatives. You're not really going to learn any new calculus or very little new calculus in this chapter, and it's pretty easy calculus. But that doesn't mean this is an easy chapter because you need to do a lot of algebra in this chapter. Well, let's try this on your screen.
Okay. Okay. So let's see, 3 and 2. X squared plus negative 2x plus negative 3x plus x. Okay.
Okay, good. Okay. All right. Well, so it looks like that went fine. Very good. This is something we actually might have talked about in the previous session, but that's the correct approach here for solving this problem. Let's see. You got x equals 3. That's good. I'll go back to my screen.
Okay.
So what you had to do here was solve a quadratic equation. And quadratic equations are not solved like normal equations. Normal equations are solved by isolating x. But there isn't actually any way to directly isolate x in a quadratic like this, so we need some other tricks. So basically the trick we're going to use here is reverse FOIL, as it's called in high school. But you remembered another trick. This would be pretty hard to reverse FOIL if you didn't see that you could factor out the 3. So that's something we talked about previously. So that was a good idea. That makes this much easier to reverse FOIL. Good. By the way, if you wanted to now, you could divide both sides by 3.
Okay.
You don't have to do this, but that just gives us a simpler equation now. Okay. Now we can reverse FOIL. Now, how do you know this is the correct answer? How do you do reverse FOIL? Well, the answer is the only way to do reverse FOIL is by trial and error. You just have to guess whether this should be plus or minus and what this number should be. And you have to guess whether this should be plus or minus and what this number should be. And you just keep taking guesses until you get something that works. But obviously, once you have a little practice, you'll start to get better judgment about getting quickly to the right guess. How do we test this answer? How do you know this is right?
We can FOIL that.
You FOILed it forwards. That's right. Remember, so F stands for first. So what would we get as our first terms?
We would get x squared.
And O stands for outer. So what do we get when we multiply the outer terms?
We get negative 2x.
And I stands for inner. So what do we get when we multiply the inner terms?
We get negative 3x.
Which we notice would add to negative 5x, which is exactly what we're looking for. And L stands for last. And when we multiply those, we get
positive 6, just
okay,
6.
Good. Now, I'm not saying you actually have to write this down every time. You shouldn't have to write this down, but this is what you have to do in your head every single time. You probably already did this. The only way to tell this is right, the only way to tell if you did reverse FOIL correctly is to take a guess and then do forward FOIL to make sure that it gets you back to where you started. You can do it in your head if you're comfortable with that, but you have to do it. Okay, good. And then you said x equals 3 or x equals 2. Were those your answers?
Yep.
How do you know that those are the answers?
Because when x equals 3, you have 3 minus 3, which is 0, and you're multiplying 0 times some number, and 0 times anything equals 0.
Good. So the key point here is if you know that a times b equals 0, what does that tell you?
If a is 0, then it equals 0. If b is 0, then it also equals 0 as well.
All right, you're on the right track. We haven't quite expressed that clearly. What it tells us is that either A or B must be 0.
Okay.
It tells us that one of these two must be 0, because otherwise they couldn't multiply to be equal 0. So this means A equals 0. So if you remember, a slightly better technique here then would be to say, actually, we don't go straight to here. What we really know first is that either this term is 0 or this term is 0. And now that gives you two simple equations that you can solve with very simple algebra. Now, maybe this problem was so simple you didn't need to write out this step, but as we go along, the problems will get more complicated. So it'll be helpful to write out this step. This is what we're really doing. We know what we're doing is we're taking a quadratic equation and rewriting it as two simpler linear equations that we can then solve by isolating x. So I think this, in the long run, this will be a safer way to solve this type of problem. Okay, but that's really just notational. Overall, you used a good approach there. That was the right way to solve that problem. Very good. So let's continue. Try this one.
Okay.
Solve for x.
Take 3 out of it. X plus 6x. Okay.
Excellent. Okay, that's very good. So those are the correct answers. That's a good process. Great.
Cool.
That was a little bit harder to reverse FOIL because there were two different signs in the factors, but you worked it out. Okay, very good. So it looks like we have that algebra down. Let's take a look at this problem. Okay, so now let's try this problem. Now, this problem is similar to the previous problems, but I'll warn you it's also different from the earlier problems. So similar but different, so give it a shot. If you get stuck, I'll give you some help.
Okay. All right. Yeah, I don't think that's correct. Okay, let's see. 5x squared plus 4x plus 1. So...
Okay, so it's good that you saw that wasn't working. How can we see that's not working? Well, remember, if we're trying, let's not quite erase it quite yet.
Sorry.
If you're trying to solve for x, that means that you need to get the equation to have just one copy of x on one side of the equation. So you can see that so you haven't actually made any mistakes, which is good. Everything you wrote down was algebraically correct. Everything you've written down is legal. It just isn't useful because it hasn't helped us to isolate x. In fact, we've kind of taken a step backwards, if you see, because we prefer all the x's to be on the same side, right? Mm-hmm. We want all the x's to be on the same side, but what you've done is moved one of the x's to the right-hand side and left one on the left-hand side. So everything you wrote here was legal, but it doesn't take us closer to solving the equation, and I think you saw that, so that's good. Okay, so if you want, you can erase those now. That turns out not to be the right approach.
Okay.
You might be able to figure out if you thought about this more, but I'll give you some help. It turns out that we still have to do reverse FOIL.
Okay.
We still have to do reverse FOIL.
Which is different. Okay.
It's just going to be harder. Why is it going to be harder? Well, because we can't get rid of the 5 in front of the x squared because it doesn't factor out. So we're just going to have to plunge ahead and factor even having that 5 in there.
Okay. Well, there's only one option.
That's right. That's the key. There's only one option for those terms.
And then, let's see. These have to be 1.
That's a good point. That's right. There's only one option for those numbers.
So 5x squared, but, okay, that's not right. Okay. 5x squared minus, oops, I think I had it right the first time. But 1x minus 1. Okay, yeah, it's the opposite. Okay, cool.
That's a good trial and error approach. And it's good that you saw, because this is more difficult, it was good to actually write out the FOIL steps. That was a good approach. Okay? And I think here's where it's helpful to have this more sophisticated approach where we set the two sides equal to 0. Good.
Okay, cool.
Okay, very good. Okay, so we ended up now here with the answer. So anyway, this is some more algebra that we're going to need in this section, a slightly more advanced reverse FOIL. So, so that would be a good thing to review again in your notes. Anyway, once I pointed out that you had to do reverse FOIL here, you used a good approach of basically just trial and error. The key that made this a little bit doable is that there was, as you were pointing out, there was kind of only one possibility for each of the terms. And then you just had to play around with the signs, plus and minus, until you got something that worked. Good, so I'll go back to my screen.
Okay.
So what made this problem more difficult than the earlier problem? Well, in these earlier problems, we were able to get rid of the number in front of the x squared by factoring. That made them easier. In this problem, we're not able to get rid of the number in front of the x squared because it doesn't factor out. But it turns out that it was still possible in this case to reverse FOIL. Nevertheless, you still should factor out this number when possible. That certainly makes our life much easier. Okay. Let's try this problem.
Okay.
So again, we're solving for x.
Okay. So, okay. Equals 0 to x equals -1, x equals -1. Okay.
Okay, good. All right, so that was another quite similar example. Okay, very good. All right, so so that will be the algebra that we need right now, and now we can go back to some calculus. Notice that those were still relatively simple to reverse FOIL because there was only one possibility for each number. Obviously, these could be more difficult if there was more possibilities for each number, but I'm not going to go into that until I take a look at the sample tests and see whether you really need that. So again, the more sample tests you can get, the better feel we can get for how hard algebra your instructor is going to give you. But for now, I'm just going to do this much, and maybe that's all we'll need. Okay, so let's go back then to my screen and move back to the calculus then. All right, so let's see. The next idea, well, actually, I changed my mind. Let's go back to your screen. I think you're still on your screen, right? All right,
Yep.
So let's stay on your screen. Scroll back up to one of those previous graphing problems where we were doing the max and the min. How about the last max-min problem we were working on? Great. So, great, thanks. Draw the tangent line at x equals 7. Draw the tangent line as a solid line at x equals 7. Okay. So you said that at x equals 7, the tangent line is downward sloping.
Mm-hmm.
So you said that that would mean that the function would be downward sloping at x equals 7, right?
Right.
But
well,
isn't that really impossible at a minimum? If the function was actually downward sloping, that couldn't really be the minimum, because if we moved to the right, it would be even lower. So the tangent line can't really be downward sloping at that point if that was truly a minimum. Maybe hit undo and remove that line. Try again to draw a tangent line. What would the actual shape of the tangent line have to be to skim a minimum? That looks better.
A horizontal line?
It really has to be horizontal, yeah.
Okay.
Okay, very good. Now let's try drawing the tangent line at x equals 8. When you're ready, take your time.
Okay. X equals 8, same thing. So, okay.
All right, so that too should be horizontal. Good.
Okay.
Let's. That was fun. So let's also draw the tangent line at x equals 9.
Okay. Another. Okay.
Okay. Notice that what we were picking out there were local maximums and minimums. So what have we learned about the tangent line at a local maximum or minimum?
It has a slope of 0, so the
That's right.
derivative is 0.
Ooh, okay, excellent. That's right. So first of all, we could say, without studying any calculus, we could say the tangent lines are horizontal at the local maxes and minimums. But then we could take that one step further and say, what does it mean to be horizontal? That means the slope is 0. Excellent. And then you took it one step further. So what is the derivative of the function at x equals 7?
It is 0.
Good, because isn't this something we were practicing in our previous chapters? What is the graphical interpretation of the derivative? What does the derivative tell you about the function graphically?
It shows you the slope of the function at a certain point.
Try that one more time. That wasn't quite the best way to phrase it.
Okay.
What's our graphical interpretation of the derivative?
Oh, okay.
You were pretty close, but
right.
It's probably better at this point to say, you said it tells us the slope of the function, but the slope of the function is not all that well defined because the function is a curve. So it's better at this point to say that the derivative tells us the slope of the tangent line at the point.
Okay.
It's because the slope of a line is very well defined. That's something that we defined clearly in high school. Okay, so what's the graphical interpretation of the derivative? The derivative tells us the slope of the tangent line. Okay, so I think you were thinking of the right thing there. So in any case, at x equals 7, as we just showed, the slope of the tangent line was 0, so the derivative is 0. So what's the derivative of this function at x equals 8?
It's also 0, because the slope is 0.
Good. So notice we could write that as f prime of 8 equals 0. Perhaps we should write that down.
Okay.
And what's f prime of 7?
Also 0.
Good. And f prime of 9? Good. Now what we're saying, I noticed that you moved the cursor over to x equals 10, but the tangent line there does not have to be horizontal. You kind of drew it kind of like it was horizontal there, but it doesn't have to be horizontal at that point. After all, take a look at x equals 6. I think you would agree to me that the tangent line is not horizontal at x equals 6.
Right.
So the endpoints certainly do not have to have horizontal tangent lines. It's the local maxes and minimums that have to have horizontal tangent lines. So basically what we've seen is what's the derivative at any local maximum or minimum?
0.
Yeah, at any local maximum or minimum, the derivative is 0. What about absolute maximums or minimums? Well, that's more complicated. We'll have to come back to that later. The situation for absolute maximums and minimums is more complicated, so we're not ready for that yet. But we have shown that the derivative at the local maxes and minimums is 0. Okay, good.
Okay.
All right, very good. So maybe now I'll go back to my screen. So what we're trying to do here now is we want to try to figure out what the local maximums and minimums are for a function. So what we need to do is identify the candidates. For local maximums and minimums. Well, obviously, one key candidate is points where f prime of x is, well, is what? If it's a candidate for a local maximum, what would be f prime at that point?
0.
Right. So these will be some of our candidates for local maximums and minimums. Now, I want to point out that doesn't prove it's a maximum or a minimum. For example, let me give you this kind of weird function. This is a little harder to see, but the tangent line here is also horizontal. Normally, the tangent line skims the graph without crossing it, but this is the one exception. In this case, the tangent line really does have to cross the graph at the point. Okay, so this tangent line is horizontal. So what's the slope of this tangent line?
0.
So what's the derivative at this point?
0.
0. But notice this is obviously not a maximum or minimum.
Mm-hmm.
Okay, so all I'm saying is these are just candidates for local maximum and minimum. Having f prime of 0 doesn't prove you're a maximum or a minimum. It's just a candidate. Okay. Now, it turns out there's another way to be a maximum or a minimum. So, is this a absolute max, absolute min, local max, or local min?
Well, that would be a local max.
Good. Right now, we're not thinking about tangent lines. We're just using what we talked about at the beginning. That's clearly a local max. However, this is something we haven't talked about before. So this is hard for me to draw, but this is supposed to be a straight line. And this is supposed to be a straight line. The point is, there is no tangent line at this point. The tangent line is undefined. Sometimes things in math are undefined. The tangent line is undefined because if you look at the left-hand portion here, it's clear that the tangent line has to look like this. But if you look at the right-hand portion of the graph, it's clear that the tangent line has to look like this. But those two things contradict each other. So there can't actually be a tangent line. There's no way for a tangent line at this point to be consistent with the points to the right and the points to the left. So here, there's no tangent line. Sometimes the tangent line is undefined. We haven't really talked about that before, but that can occur. Basically, so what does that tell us about the derivative at this point?
There is no derivative. It's undefined.
That's right, because remember the derivative is the slope of the tangent line. If the tangent line is undefined, then the derivative is undefined. So the derivative is undefined at this point. Basically, intuitively, derivatives are undefined when the graph makes a sharp turn. Do you see why I would call this a sharp turn?
Yep.
Whereas all the graphs we've seen before were smooth. Do you see where I would say this is smooth, whereas this has a sharp turn? Yeah. So it's, again, we're not going to try to give technical definitions. You kind of know it when you see it. If there's a sharp turn, the derivative will be undefined at the turn. If the graph is smooth everywhere, then the derivative is defined everywhere on the interior of the graph. Okay. So anyway, we decided the derivative is undefined here. But it's still a local maximum, right?
Yep.
So that gives us another candidate.
Okay.
For local maximums and minimums. Points where the derivative is 0 can be local maximums and minimums, but points where f prime of x is undefined can also be maximums and minimums. They don't have to be maximums or minimums, I don't think. No, they don't have to be maximums or minimums, but they're candidates. They're candidates for maximums and minimums. Okay. And turns out these are the only candidates. The only candidates for local maximums and minimums are points where the derivative is 0 or undefined. The reason why these are the only candidates is because of the definition your textbook uses for local maximums and minimums. So because of the definition they use for local maximums and minimums, that seemed a little bit of a weird definition, but the advantage is that gives us a nice simple theorem here. The theorem is that the only candidates for local maximums and minimums have to be points where the derivative is 0 or points where f prime of x is undefined. So because these two types of points are so important, the mathematicians give these two types of points a special name. These are called the critical points.
Is that the same thing as a critical number?
Yes. Maybe I should use that term instead. Is that what your textbook actually calls it? Let's see. Okay, yeah, my mistake. I'll call them the critical. I kind of like critical points, but I'll call them the critical numbers.
Yeah, I was just wondering if it was the same.
Yeah, so that's the same.
We can call it either or, whichever.
Well, the point here is, what are the critical numbers? The critical numbers are the inputs for these points. The x values. The critical numbers are the x values for the points where the derivative is 0 or the points where the derivative is undefined. So that should probably be memorized. Okay, so if you're at a critical number, what's the derivative?
0.
Or?
Undefined.
Yeah. If you're at a critical number, you know the derivative is either 0 or undefined. Okay? So how is this going to be helpful to us? Well, now we have a method for finding the local maximums and minimums. All we have to do is find all the points where the derivative is 0, and then find all the points where the derivative is undefined, and we know that those all are the only candidates for local maximums and minimums. Okay. And then we can check whether they really are maximums or minimums. All right, so next, maybe we should talk a little bit more about what it means. How can a derivative be undefined? There's actually a bunch of different ways a derivative can be undefined, but I think there's only one that's going to come up in your class. Can you think of any points where this derivative is undefined? Any inputs where this is undefined?
When x equals 3.
That's right.
Yeah.
Good. I'm sorry I interrupted you. How do you know that it's undefined there?
Because then you have 1 divided by 0, and that is undefined.
That's right. Okay, perfect.
Indeterminate.
Perfect. Undefined. Actually, undefined is the correct term here. Okay. Indeterminate refers to limits. So undefined would be the correct term here. Okay, very good. There's other ways that derivatives could be undefined, but based on what I've seen so far, I don't think we need to cover those. So this is the only one that we'll need to get into right now.
Okay.
What would be then, so first of all, what's the method then for finding where the function is undefined? Well, first of all, would you agree if there's no denominator, then it can't be undefined according to this approach, right? Because remember, the only type of undefined functions we're going to deal with is when the denominator is 0. So for our purposes, if there's no denominator, we know the function is going to be defined everywhere. Now, since there's a denominator here, what would be the technical algebraic way of finding where this is undefined? Well, I would actually write it out like this. F prime of x is undefined where x minus 3 is 0. And now that gives us an equation that we can solve. So then we can say f prime of x is undefined where x equals 3. And now we're done. So this is basically what you did in your head. But as the problems get more difficult, it'll be better to actually write it out like this. So this will be the more technical, careful way to figure out where the function is undefined. You start by saying it's undefined where the denominator is 0, and then you can use algebra to try to figure out if there's any points where the denominator is 0. Okay, good. One moment. Okay. Okay, I have that written down.
Yep.
Okay, so I think this problem, I'll try to demonstrate what I think is a good approach here. So we're trying to find the critical numbers of this function. Well, the critical numbers are based on the derivative, right? So the first thing we have to do is figure out f prime of x. So you can go ahead and tell me what would be f prime of x here.
That would be 6x minus 7.
Okay. Now the next thing I would say is we can call the critical numbers c. Well, what do we know about f prime of c? Well, first of all, are there any points where this function is undefined? Well, no, because there's no denominator, right? We can trust that if there's no denominator, it's not going to be undefined. So the only other possibility then is what's f prime going to be at the critical number?
0.
So this is the first thing I would write down.
Okay.
We're going to use c to stand for the critical number. Well, we know that f prime of c is 0. What we're trying to do is develop a systematic approach for these problems. So now I want to write something down on the left side of the equation. What is f prime of c? Well, I can use this expression right here to write something down for f prime of c. F of x is 6x minus 7. I'm sorry, f prime of x is 6x minus 7. So f prime of c is 6 times c minus 7. And the right-hand side here is still 0. And now we can use algebra to solve for c.
Okay. So c equals 7 over 6.
Now there will be some problems where there's more than one critical number. But in this problem, it looks like there's only one critical number. Okay, so we have that our critical number is 7/6. Oh, I guess we're done then. So we're done with A. We've discovered that this is the only critical number. All right. So I think this is a good systematic approach for these types of problems. So we'll try to use this notation. So notice the first step on these problems, since they involve derivatives, is to calculate the derivative. That's the calculus portion. And the calculus for this chapter should be really easy, or relatively easy, because I think it's just going to be practicing the calculus we already learned in the earlier chapters. And I think we made good progress on that. Notice the rest of the problem was algebra. That's why I was saying there was a lot of algebra here. This algebra was pretty simple, but the algebra can get more tricky as we go on. Okay, now let's do something else here. Let's try to interpret this. Remember what this means is this is our candidate for a local maximum or minimum. This is our candidate for a local maximum or minimum. So I think it would be good for our understanding here then to graph a bunch of these. So I'm going to graph the function. The function was 3. You can try. Do you have your calculator with you?
Yep, I'm
You
grabbing
can try
it.
following along. Okay. By the way, notice we're not graphing the derivative. We're graphing the function. And now I'm going to go to zoom standard to make sure that I have a standard zoom. And that'll automatically take me to the graph.
Cool.
Are you there?
Yep.
Good. Now I'm going to go to trace. And I'm going to type in 7/6. Notice that I'm typing that in for x here.
Mm-hmm.
And notice, if I hit enter, notice that that moved the cursor to 7/6.
Yep.
And is there anything interesting about that point at 7/6 on the graph?
Yep. It looks like 7/6 is the absolute min and a local min.
There you go. Okay, so it looks like this method actually works. Remember, it wasn't guaranteed that this would be a local max or min. It was only a candidate, but now we can confirm that it really was a min. And actually, if you look at the graph, you can see there are no other local maximums or minimums. There's no. It just goes on to infinity on both sides.
Mm-hmm.
So this really was the only candidate. So I think for right now, probably we should graph all of the examples to get a better understanding of these. So we'll keep going through that process. Okay, very good. So continuing. Okay, so this is part B for the same problem. Find the critical numbers of the function. So why don't you give this problem a shot and try to use the same approach and notation that we were just talking about.
Okay. Okay. Derivative. X plus 4. Okay. So now we say f prime of c equals 0.
That's the definition of a critical number. Good.
Mm-hmm. So now we can use sorry. 10c plus 4 equals 0.
Good. You've already written that underneath f prime c, so you've shown that they're equal to each other.
Mm-hmm.
Good.
So 10c equals 4. C equals 4, 10 equals negative 2/5. So the derivative is 0 at negative 2/5.
Great. So what's the answer to the question?
The critical number is negative 2/5.
Excellent. Good. By the way, do the critical numbers represent inputs or outputs for the function?
They represent inputs.
You can see that because you put it inside the parentheses in your function notation. Okay, good. By the way, one thing you should mention to yourself is, how do you know that this derivative we also have to check whether the derivative is ever undefined. How do we know that this derivative is not going to be undefined anywhere?
Because the graph is going to be smooth, and we can, I guess we could check this.
How do we know it's going to be smooth? The key thing is, remember that in your class, the only type of function that's ever going to be undefined anywhere is functions with denominators.
Okay.
So what we want to check for is just check if there's a denominator.
Okay.
And who are we checking for the denominator, f or f prime?
We're checking f, the function.
Well, careful. Remember, we're looking for critical numbers. What's the definition of a critical number? A critical number is a number where
where the critical number is the point of a function where the derivative is 0.
Good. Or
So,
undefined.
or undefined.
Who's undefined at the critical number? What is undefined at the critical number? The derivative or the function?
That would be the derivative.
That's right. So who do we have to check for a denominator when we're looking for critical numbers?
We have to look at the derivative.
Yeah, not the function. A common mistake people make in calculus is they confuse the function and its derivative. The critical numbers are not the points where the function is 0. They're the points where the derivative is 0. The critical numbers are not the points where the function is undefined. They're the points where the derivative is undefined. So we just have to check the derivative to see if that has a denominator, to see whether it's possible for the derivative to be undefined. Okay, now it is true that it turns out this function is smooth, but you can't really, we haven't gone over techniques for checking whether things are smooth without graphing them. So since we haven't looked at the graph here, what the actual method we're going to be using here is to see if there's a denominator for the derivative. Okay, so go ahead and try this on your calculator. Try graphing that function, and as you go, you can talk me through what you're writing down.
Okay. I'm going to y equals, and I'm going to put in 5x squared plus 4x. So we're going to graph the function. Then I'm going to go to zoom standard. That's going to graph it for me. All right, and I'm going to trace over to -2/5. And it looks like at -2/5, that is the absolute min and a local min.
You can see the blinking cursor is there, and it looks like it's at the absolute and local min. That's right. Okay, so that's consistent with what we would expected here for a critical number. And notice it looks like it's the only local max or min, but that's also consistent because that's the only candidate. Okay, all right, that was a good process. Very good. So I'll go back to my screen. So what's the definition of a critical number?
A critical number is a point of it's a point on the function where it's a point on the function where the derivative is either 0 or undefined.
Excellent. That's exactly right. So it's good that you took your time. It's a little difficult at first. It's good that you took your time and came up with the exact right definition. Okay, so now let's do part C for that same problem. We're still trying to find the critical numbers.
Okay.
Let's try this. So we want to find the critical numbers for this function.
Okay.
So this is a little harder and more difficult than the previous problems, but as much as possible, we want to try to use a similar notation and approach.
Okay. Okay. Wow.
see. I'm confused. I'm not... It looks like you've written down f of x twice.
Yeah, I rewrote the function.
Mm-hmm.
And then
I'm not sure, but I'm not sure how you... Oh, I see what you did. You multiplied everything by 3?
Mm-hmm.
Okay. Well, there's a problem with that. So basically what you did is you multiplied everything on the right side of your equation by 3, right?
Mm-hmm.
Well, that's fine if you're going to multiply the left side of the equation by 3. Otherwise,
okay.
it's not a true equation, right?
Okay.
All right. So it is, if you wanted to multiply the right side by 3, you could, but only if you then multiplied the left side by 3. But then that wouldn't do you much good because then you would have 3 times f of x on the left-hand side, and that's pretty complicated. Okay, so it turns out that the multiplying by 3 technique doesn't really help us here.
Okay. Let's see if I can figure something else out. Okay. So well,
that's a good step. Excellent. Good.
Okay, so this is just 5 x squared okay.
Good.
And then now we know that prime of c is 0, so
Good.
we can do okay. Okay, so we need big negative. Okay.
Okay, good. All right, so you can see this was a step up in difficulty, but now we saw how to do it. You can see why we had to do that algebra review earlier, and you can kind of see why I was saying the main challenge in these problems is not really the calculus so much, but the algebra. The calculus here was fairly standard from the earlier chapters, but we have to remember this high school algebra. Okay, good. Notice that, why were you multiplying everything by 3? You were trying to get rid of the fraction. That's usually a good instinct, but notice that the fraction here didn't really hold any terrors for us, because once we took the derivative, it kind of evaporated. So, so that turned out not to be a huge issue in this case. Okay, good. So now let's confirm this on your calculator.
Okay.
So try talking me through the steps you're going to go through to evaluate this on your calculator.
So I'm going to try and graph the function. So I'm going to get a y equals. I'm going to type in. I'm going to use parentheses just in case, but 5/3 x cubed minus 2x squared minus x plus 1. And then zoom standard just to make sure.
Good. Although, since you haven't changed your zoom since the last time, you already know it's still standard.
Okay. So, I'm going to zoom in. Can't see it very well.
Maybe before you zoom, you should actually go to the point you want to zoom in on.
Okay.
So let's hit trace. What's the first point that's interesting for us to check now?
-1/5.
Good. So
Oh, okay.
how would you classify that point?
It looks like that point is. Let me zoom out.
You actually probably wanted to zoom in.
Okay. Well, it looks like that is a local maximum.
Just like we might have expected for a critical point.
Mm-hmm.
You can see the cursor is up here at the top. All right, so what's the next point to check?
1.
Good. Here we have 2 critical points.
Mm-hmm. And at 1, it looks like the function is, well, sorry, not the function. It looks like at 1, there is a local minimum.
Yeah, so the function is at a local minimum. Good. So the critical number technique really is allowing us to pick out candidates for local maximum and minimum. And you can also see, if you zoom out again, that there are no other maxima or minima. It just goes off to infinity in the other directions. Those really were the only candidates, just like the theorem from the textbook said. Okay, very good. Okay, good. So I'll go back to my screen. All right, so we did have a little trouble with this at first. What made us think that we could multiply by 3 here? Well, suppose that you had if you wanted to multiply this by both sides by 3 here, you'd have to get this equation.
Mm-hmm.
You can't multiply the right side of the equation by 3 unless you multiply the left side of the equation by 3. But that's a step backwards because now f of x is not by itself, so we don't want that. Here's what you were probably thinking of. Let's say this was the equation. Now what happens when you multiply both sides by 3?
You would get 5x cubed minus 6x squared minus 3x plus 3 equals 0.
Why is it still 0 on the right-hand side?
Because you're multiplying 3 times 0.
That's right. So that might have been what you had in the back of your mind. This is the kind of this is a situation where multiplying both sides by 3 would be quite helpful. Once something is solved for 0, then it's a good idea to multiply by 3 here because that's not going to mess us up on the right-hand side of the equation. There's other times when it might be helpful to multiply both sides by 3 as well. All right, but in any case, this was not a situation where that was a useful technique. Okay, good. So looks like we're on D. Okay, let's try this one. Good. Why is this a good time to divide both sides by 3? Because notice now you have a 0 on one side. Good. And 0 divided by 3 is still 0.
Okay, so now I'm going to graph the function. Type in x cubed plus 3x squared minus 24x. I'm going to zoom standard that one. Okay, this is a crazy looking function. Okay, so let me zoom out.
Now, when you're zooming, you have to tell the calculator what point to zoom around. So actually a better process is first go to the point you care about and then zoom. Okay. So the best thing to do here now is to hit trace, and then what number should we enter in?
Use -4.
Good. Then hit enter. Now I think I can't actually see the cursor, so it looks like x equals -4 is off the screen. But now you can go to zoom. We want to zoom in around that point. And now, I can see now it's up here at the very top. Now you hit enter again to tell the calculator that we're already at the point we want to zoom in on.
Right. It looks like maybe I made a mistake.
Me too. This isn't working out so good. What's going on here? Well, actually, let's try trace again. So trace -4. This is a pretty weird graph, actually. The calculator's having trouble with it. So. Okay, well, the problem here is that it's that 24 is making the x values here very big. So they're moving off the screen. So I think on this problem, you can't use the zoom. In order to get this to work, you'd probably have to adjust the window values. But you know, your instructor's not testing this directly. We're just doing this as a backup to improve our understanding. So when it's hard like this, we can just say, well, forget that one. Okay, so we won't worry about the calculator for this problem, since it was too hard to make. It was too hard to get the window zoomed into the right place. We're just going to use the calculator. What is an easy way to give ourselves some extra intuition? In any case, I think that you did get the right answers here. Good. So let me take another look at your screen. Okay, very good. One thing that gave you a little pause on this problem, perhaps, we've learned how to do reverse FOIL when you can't get rid of the number in front of the c squared. But that doesn't mean you shouldn't get rid of the number when you can. So it was good that you saw here that in this case, we really could get rid of the 3 in front of the c squared. We always want to get rid of that number if we can. So it was good that you did that. Okay, so anyway, we ended up with the right answer there. That's good. So I'll go back to my screen. So let's see, that was D. All right, so again, let's find the critical numbers.
lengthy possibilities. I don't think it really works. So yeah, that doesn't work. Okay, so we have to use a different method.
Okay. Well, I think what you actually kind of just proved there. Okay. What's actually going on here is this problem has no critical numbers.
Oh, okay.
That's why you're not getting an answer. Notice that you can't find any way to make it work. That's because it actually has no critical numbers. Okay, I didn't realize that was what this problem was like, though. I don't know if your instructor is actually going to test you on that. But just for the heck of it, let's try graphing this.
Okay. So because we couldn't factor,
that was a clue that there were no critical numbers. Yeah. It doesn't quite prove it. You actually have to use the quadratic formula to prove that there's no critical numbers. But I don't think your instructor would actually assign this question. I didn't realize there were going to be no critical numbers. But it will be interesting here to draw the graph anyway.
Okay. All right. So zoom standard. Okay, so I see the graph, and there would be no local min or max. So
yeah, that's the key. If you look at the graph, it just goes off to infinity in both directions. It never Notice the graph has to turn around somewhere to have a local minimum or maximum. It never turns around. So it shouldn't surprise us that there were no critical numbers, because the critical numbers are the candidates for local maximums and minimums, and there is no local maximum or minimum. If you zoom out on the graph, you'll see that it still never turns around. It just goes off to infinity in both directions.
Right.
Okay, good. All right. That was an accident to assign this. I didn't realize that this problem had no critical numbers. I think your instructor probably wouldn't give you a question like that. But anyway, we got a little insight into what was going on in that problem. Okay, so let's continue. Let me write something else down here.
So on that graph, there is a point where the slope is 0, but it's just not a critical number, right?
I'm glad you mentioned that. That's good that you're looking at that. What point do you think that the slope is 0 at?
Let me zoom back in.
Eyeballing it, where do you think the slope is 0? About what x coordinate?
Actually, now that I look closer at it, I don't think that's true.
So it's basically around x equals 0, right?
Right.
So let's trace x equals 0. Then we can go to zoom. We can zoom in. I'm going to try zooming in around that point again.
It just looked like it from afar, I guess.
That's right. If you really zoom in, you can see it's upward sloping at that point. So that means there really is no point where the tangent line is horizontal. If you zoom in enough, it's very clear that the point is upward sloping at that point.
Okay.
Okay, good. So that was a good thing to notice there. Yeah. So it really turns out there really is no critical number there. Okay, good. So I think we got some insight from that. But you might want to make a note in your notes. I think that's a little harder than your instructor would assign you. Okay. So let me write down this problem. Okay, so now let's try this. So the algebra on this problem is going to be a little different than before. So we'll have to see if we can adapt and figure out how to do the algebra here.
C squared, C, C, and 1.
So I think that's another one that doesn't really factor, right?
Right.
All right. Yeah, I didn't test all these out ahead of time. So it looks like that's not erased anything quite yet. Okay. So it looks like so you're not going to be able to do reverse FOIL. What that basically means is that c squared plus c minus 1 is never 0. C squared plus c minus 1 is never 0. But there's still a way for the derivative to be 0.
Right. So when c equals 0,
then the derivative is 0.
Right.
Yeah. C squared plus c minus 1 will never be 0. That's why it wouldn't factor. You could confirm that using the quadratic formula. Okay, good. So what's the critical number?
0.
Good. Okay, good. So again, I don't think your instructor would give you a problem that doesn't factor, but this is still a good problem for your notes because I do think they might give you this algebra. So the main reason I wanted to go over this problem was the algebra here that you figured out correctly. So the key thing here is that you saw all the equations we had before were quadratic equations. But here you got a cubic equation with c cubed, but you figured out how to deal with it. You dealt with it by factoring out a c. So that is something I think that would be fair game for your instructor to use. So it's good that you saw that you had to factor out the c here. I don't think your instructor would actually give you something then that wouldn't factor. But at least we got to practice factoring out the c. So, so what's the critical number?
0.
Yeah, and we might as well check that on our graph now, on our calculator.
Okay, so y, so I got a 3x to the 4th plus 4x cubed minus 6x squared, and I assume standard. Then I'm going to trace at 0, which I think is already there, and I'm going to zoom in. Yep, it looks like at x equals 0 there is a local maximum, and which means the slope is 0, which is what we got. We got c equals 0. It's a critical number, and when c equals 0 we have a local maximum and no slope.
Good, but I'm worried because it looks like there's also a local minimum to its right.
Mm-hmm.
Which there shouldn't be because we only had one candidate.
Ah.
If you see what I'm saying.
Right.
So maybe we actually missed a possible value here. So let's go back. I'm going to go back and take a look at your screen again. Is it? Let's see.
How about when that's a positive number?
Okay, yeah. So even though this doesn't factor, you could solve it using the quadratic formula, and you would actually get an answer. There are some things that sometimes you have to use the quadratic formula when things don't factor. You actually can get an answer here using the quadratic formula, but we won't worry about that. I don't think your instructor is going to give you that. Okay. So the only reason I was doing this is I wanted to go over the algebra here of factoring. You do need the step where you factored out the c, the step where you factored out the 12c. That's the part of the problem that I think your instructor would test. I don't think they're going to give you problems that don't factor. You don't need to worry about the fact that this didn't factor, but they could give you a problem where you had to do that algebra of factoring out the 12c. So that's the only part to worry about on this problem. You could use the quadratic equation here, but I don't think your instructor expects you to do that. All right, so let me give you one more problem. F G So again, let's find the critical numbers.
Three c squared, 3c. Okay. Okay, I'm gonna graph this. Okay. So I'm going to graph function x cubed minus x squared.
Plus x squared.
Oh, yeah, plus x squared. Plus x squared minus x. X cubed plus x squared minus x. Okay. Assume standard. And trace. It's 1/3. And it looks like at 1/3 we have trace 1/3. Okay, yep. We have a local minimum at 1/3.
Look good?
And then,
Good?
Yeah. And then at -1, we have the local maximum. So it checks out.
That's right. And notice also, as you can see more clearly if you zoom out, those are the only local max and minima. Because other than that, it just goes off to negative and positive infinity. So the theorem works. The only candidates for local maximums and minimums are the critical points. Okay, good. Oh, one thing that we've been forgetting to check here is we should also be...
Okay. A critical point is where the slope is 0. So, and it's
the
also
slope of what?
The slope of the function.
That's right. Or what's another way of putting that?
The slope of the tangent line at a point.
That's right. However, that's right. But let's put it in a way that's more useful for these problems. What is the critical point? Define the critical point in terms of the derivative.
Okay. So the critical point is when the derivative is 0. Or undefined.
That's right. So what we've been sloppy, we've been forgetting to check for the undefined. So what do we have to check here to see whether we have to deal with that undefined issue?
Okay. We would have to see if the function is if the function's continuous at the critical
Let me help you with
point.
that. I think you might be misremembering that. So remember, what's the definition of the critical point?
The critical point is the point where the critical point is the point where um, the I guess uh, the critical point is maybe I'm not sure.
How did you find the critical point on this problem?
I set the derivative to 0.
So what's the definition of the critical point? The critical point is the point where...
The critical point is the point where the derivative is 0.
Okay, good. That's right.
Yeah.
So unfortunately, sometimes people start to do these problems mechanically without thinking about what they're doing. Why do we keep writing down f prime of c equals 0? Because that's the definition of the critical point. The critical point is the point where the derivative is 0.
Mm-hmm.
Or
where
the derivative is undefined.
Mm-hmm.
The critical point is the point where the derivative is 0 or undefined. That's right. That's a good way to put it. The critical point is the point where f prime is 0 or undefined. So we've already figured out where f prime was 0. Now we have to ask whether f prime is ever undefined. Well, point to our formula that defines f prime.
Right here?
That's it. Yeah. So we need to know, is that formula ever undefined? Well, do you remember we said that in your class, the only formulas that we're going to have to worry about that are ever undefined are when you're dividing by 0. Notice this is not really directly related to the idea of being continuous. We didn't really use that continuity idea here. The derivative will be undefined if it involves dividing by 0. But you can see from that formula that our derivative here does not involve any division. Mm-hmm. So we don't need to worry about that. All right, the only reason I'm mentioning that is that we will eventually get to problems where the derivative is sometimes undefined. We're working our way up to that. So we do want to keep that in the back of our mind here as we go. Okay, so what is a critical point?
Critical point is where the derivative is 0 or undefined.
Okay, good. And why do we care about the critical points? Well, those are the candidates for local maximums and minimums. Let's go back to my screen to finish up.
Okay.
So here's some of the key ideas from today's lesson. The candidates for local maximums. Oh, so the point is the critical numbers are where the derivative is 0 or undefined, and those are the candidates for local maximums and minimums. What's next? Well, remember we said that the critical numbers are the candidates for local maximums and minimums. And I kind of said to you briefly that the situation for absolute maximums and minimums is more complicated. So that's kind of the next thing we have to get into. The next topic would be how do we extend this to thinking about the absolute maximums and minimums. Let's try the problem.
Okay. Okay.
Okay, good. So what is a critical number?
A critical number is a point where the derivative is either 0 or the derivative is undefined.
Good, excellent, good. So that's important to understand. Why are the critical numbers interesting to us?
Critical numbers, because it can show us where a potential local min or max is.
That's a good answer. Excellent, very good. We didn't quite hammer that home last time, so that's good that you're seeing that. The reason we're practicing this is because these are the candidates for local maximums and minimums. The way you phrased that was very good. You said, I think, potential maximums and minimums. That's a good point. They're not guaranteed to be maximums or minimums, but they're potential. So that's good that we're seeing that. Okay, and we know we care about that because, for example, if this function represented costs, it would be nice to know where the firm could minimize its costs. Or if it represented profits, it would be good to know where the firm could maximize its profits. So in general, it's interesting to see where maximums and minimums are for a function. Or if you're just trying to graph the function, it's helpful to know where the maximums and minimums are as well. Okay, good. So what is the graphical interpretation of the derivative?
As the function increases by 1 unit, the graphical interpretation of the derivative is the slope, I guess.
Good.
Or is there? Yeah.
Yeah, that's what I was going for. Whose slope?
The slope of the tangent line at a certain point on the function.
Good. The slope of the tangent line to the function at a certain point. Good. Now, it kind of also tells you the slope of the function itself, but in this class, we start by focusing on how it gives us the slope of the tangent line. Okay, what about that other stuff you were saying? Well, that was another way of interpreting derivatives. The derivative also tells you how much the function changes when you change the input by 1 unit, approximately. But in this chapter, we're not focusing on that interpretation so much. Obviously, as you've seen, we're focusing on graphical interpretations here. So to review one more time, what is the graphical interpretation of the derivative?
It is the slope of the tangent line to the function. The slope of the tangent line to the function.
That's right. Good. And we've drawn some pictures of that in the past, so hopefully we have, that shouldn't just be words, we should have a mental picture to go with that idea. Remember that in the previous chapter we did exercises where we had to find the equation of the tangent line, and whenever we did those, we always drew the graph and drew the equation of the tangent line, and showed that the derivative was the slope. Okay. All right, that's good. I'm going to go back to my screen. Okay, so as usual, we always start by quizzing ourselves on the old materials. That was a redo of one of the old problems, and you got that right. So now we can just go on to the new stuff. Okay. So again, we're going to have to shift back and cover some high school algebra now, and then we can continue. Let's try this. Okay.
Okay.
Okay, very good. So we've learned how to solve two different types of equations. One thing we've learned how to do is solve quadratic equations. And we've seen quadratic equations require special techniques, like reverse FOIL. But this is not a quadratic equation. This was just ordinary equation. So to solve this, step one, get all the x's on the same side. Well, they're already on the same side. And then the next step is we need to get there, combine the x's so there's only one x term. And you saw that the key thing here is that before you could do that, you had to get rid of the parentheses. And what was the technique you used for getting rid of the parentheses? The distributive rule. So that was the main thing I wanted to review here. Oftentimes when you're solving equations, you have to get rid of parentheses. And a good way to get rid of parentheses is to use the distributive rule. And then you can combine the x terms and then get the x by itself. So we got that right. That's good. That was just to review. You can get rid of parentheses using the distributive rule. Now, there's some problems where you want parentheses, but on this problem, we couldn't get the x by itself unless we got rid of the parentheses. So that was a good process. I'll go back to my screen. What's this?
25.
What's this?
36.
What's this?
0.
Good. And before I forget, this is not directly relevant, but how could you simplify this?
0.
That's right. Okay. Okay, excellent. So just to review a little squaring, there's one important lesson here. Notice that when you square something, can it ever become negative?
No, it cannot.
All right, so that's an important point. You can't, when you square something, it can never become negative. Anything you square will be positive except 0, which becomes 0. All right, so that might seem obvious, but that'll turn out to be important. Anything you square is positive except for 0, which squares to become 0.
Okay.
All right. Let's try solving this equation. You can solve this on your screen.
Okay.
We want to solve for x.
Okay.
Excellent. Very good. That's good. All right, that's a very good method. The way you wrote your answer is perfectly fine. In this chapter, it'll be more helpful to list all the solutions separately. So let's list them as x equals -3 or 3, rather than condensing them. Your notation is correct. It'll just be more helpful in this chapter to write it as x equals 3 or x equals -3. All right, this is an excellent solution. So as we've talked about, a good way to solve quadratics is reverse FOIL. That's perfectly good. That's a good approach. Now, this particular type of quadratic, there's another approach which is better for this chapter, because this particular quadratic, you kind of can get the x by itself, which you can't do in a normal quadratic. So let's try an alternative solution in addition to what you wrote. Let's move the 9 to the right-hand side. Great. Now, if x squared equals 9, what are the possible, I guess you can, what are the possible values of x then?
3 or -3.
Basically, you took the square root. So you get the same answers here. Right. Okay. If we remember that we're to consider both the positive and the negative square root. It turns out that in this chapter, that second method is going to be more useful to us. So your first method is a good one, but in this chapter we're going to try to use that second method instead. We'll see how it's more helpful on some problems. Notice though, if you use the second method, it would be easy to forget the -3 answer, right? So it's important to watch out. Remember that there's both positive and negative square roots, because that is a possible downside of using that approach. If x squared equals, let's see, if x squared equals 25, what could x be?
X could be 5 or -5.
Or -5. It's just important to keep that in mind. But notice you didn't have to do reverse FOIL to figure that out, did you? So it really is simpler to think through it that way. Okay, good. All right, so I'll go back to my screen. By the way, why was there a simpler method on this problem, but there wasn't a simpler method on the earlier problem that I gave you, this one up here, 3x squared plus 2x minus 1. Well, the difference between this quadratic and this quadratic is that this one has this x term and this one doesn't. So normally when there's this x term, you do have to factor or use reverse FOIL. And if there's only an x squared in a number and no x term, then we have that simplified approach.
Okay.
Good. So maybe the best way to write out this problem that we just did then is it's a little hard to write this out accurately, but that's okay. We're seeing what the right answer is. Okay, so we'll just go back. We'll go back to another problem. So let's try this. Okay, this one is similar to the previous problem, but also a little different. So we'll have to think it through. So let's try this.
Okay.
Right, we're solving for x. Good.
Okay. Oh. You can't take the square root of a negative number.
That's right.
So, okay.
Let me give you some help with that. So actually your solution was good. Maybe you can hit Control Y and put it back in there. Command Y. Does that work on this program? Redo? Oh, it's Shift Command Z. Okay.
Shift Command Z. Okay.
Okay, good. So anyway, you're right. There is no such thing as the square root of -16. But you didn't make any mistakes. That just means that this equation has no solutions.
Okay.
So we could say the equation has no solutions, or we could say, yeah, the equation has no solutions. There are no values of x that would make x squared plus 16 equal to 0. So the way you solved it was fine. It's just that when we get to a point where we're taking a square root of negative number, we have to recognize that doesn't mean we made a mistake. It means that there are no solutions.
Okay.
Okay, good. We should have been able to see that from the start because remember, we're trying to add something to 16 to make it equal 0. But when you square a number, it always comes out positive, right?
Mm-hmm.
Well, a positive number plus 16 could never equal 0.
Right.
So we could kind of see from the start that this equation was written down by someone that didn't know what they were doing. All right, so okay, so we can see here that there was no way that there was going to be a solution, but the way you proved it was a good approach. we proved that the only way to solve it would be to take the square root of a negative number, which means there's no solution. Okay, so for example, suppose that x squared plus 8 equals 0. If x squared plus 8 equals 0, what could x be?
There's no solution.
Because you can't, if you square something, it'll be positive, and then if you add it to 8, there's no way it could be equal to 0. Okay, very good. I'll go back to my screen. We've already seen that it's possible for an equation to have more than one solution, right? For example, when you solved this equation here, there were two solutions, 3 and negative 3. Some equations have 3 or 4 solutions, so it should not flabbergast us to discover that some equations have no solutions. And that's what we're seeing here as well. An equation could have any number of solutions, including 0. Okay, so now let me try this. Let's try solving this equation.
Okay. Zero. Okay. Oh. Seashells. Okay, so 4 minus 4. Yep. Yep. Okay.
Okay, that was a very good approach. You expanded out the square. That was a good idea. Then you factored. That was a good idea. And you did something else we haven't talked about, but it's good you see you could do this. You checked your answers by plugging them into the equation. We could have been doing that on all the problems we've been doing so far. You can always check your answers by plugging them into the equation. We've been trying to save time by not doing that. But it's good that you know that you can do that. You should always know whether you've answered the question correctly when you're solving for x, because you can always plug it into the original equation. So that's good that you saw that we could do that here. Okay, very good. So that's an excellent solution. That's very good. Again, I'd like to show you an alternative method that might be better in this chapter, but that was a good approach. The alternative method here, let's take the square root of both sides of that equation.
Okay.
And now you could factor again, but do you remember we've learned an alternative way to solve an equation that's like this?
Yes.
There's nothing wrong with factoring, but I think it'll be a little bit better in this course to use this alternative approach.
Mm-hmm. Yeah, I'll try and get used to using it. I keep forgetting right now. Okay. X equals 2 or negative 2.
Okay, great. I think those are the same answers we got before, right? All right, so I just wanted to point out, notice when something's being squared, how can you get rid of the square root? That didn't quite make sense. When something is being squared, how can you get rid of the square?
We can take the square root of both sides.
That's right, yes. That's a general rule of algebra. The rule of algebra is that you get rid of something by doing the opposite. So you can get rid of a square by taking the square root. Okay, so your original approach was a good one, but going forward, the way we solved it the second time will maybe be a better way for this chapter. Okay, good. I'll go back to my screen.
Okay.
Now let's solve this equation for x.
Okay.
Excellent. Good. Okay, great. So you got to a point where you'd have to take the square root of a negative number, which means there's no solutions. Very good. So that just means there's no values. There's no value of x that would make x squared plus 9 squared equal to 0. There are no values of x that would make x squared plus 9 squared equal to 0. Good. That's, excuse me, that's what we were going for. So I'll go back to my screen. Try solving this equation.
Yeah. Okay.
Good. Good. So the first thing we had to do there was get rid of the simplify by getting rid of the denominator. Well, a good rate to get rid of the denominator, as you saw, is to multiply both sides by the denominator. So that was a good approach. Okay, I'll go back to my screen. Let's try solving this equation for x.
Okay. Should I write out each interval, each little step, or can I just go like this?
If you're confident, you can just move on. But tell me verbally, how did you get from the first line to the second line?
Okay, I'm just going to multiply each side by the denominator. So and then that'll cancel it out on this side, and then on this side it's multiplying it by 0. So it's just going to be 0.
Okay, very good. That's good.
Okay.
That was very good. Okay. So notice that the big complicated denominator here turned out to be kind of a distraction. It wasn't really involved in the solution at all because when we multiplied by that denominator, it disappeared. After all, if you think about it, this is just common sense. The only way, would you agree, the only way a fraction can be 0 is if the denominator, no, let's try again. The only way a fraction can be 0 is if the numerator is 0.
Right.
So the denominator here is just kind of irrelevant, which is kind of what you proved. The only way to make this fraction 0 is to make 2x plus 5 equal to 0, and then it doesn't matter what the denominator is. The denominator could be 72 billion, doesn't make any difference, because what's 0 divided by 72 billion?
0.
Yeah, so that it makes sense that we ended up just focusing on the numerator. And you can see that technically because you got rid of the denominator by multiplying both sides by x cubed plus x minus 4. Okay, very good. All right, so that was another technique that we needed there. Okay, very good. So it looks like that was all algebra that you were already comfortable with. That's excellent. So let's just move forward and go back to the calculus.
Okay.
So let's see. What have we been talking about so far? We've been focusing on how to find candidates for the local minimum and maximums. How do we find the candidates for local minimums and maximums? What are the candidates?
We find the critical numbers.
That's right. They're the critical numbers. And what are the critical numbers?
The critical numbers are the points on the function where the derivative is either 0 or undefined. I think. Yeah, that's right.
Yep, that's exactly right. Well, I think we've done a good job on that. I think we've learned how to do that. So now it's time for the next topic. Logically, what we have to do now is think about how to find candidates for absolute maximum and minimum. So what we're going to be focusing on now is how to identify the candidates for the absolute maximum and minimum, which in some ways might be more interesting. After all, if a firm is trying to minimize its costs, it wants to find the very lowest place to minimize its average costs. And if you're trying to maximize your profits, you want to find the absolute maximum of the profits, not just some local maximum that's inferior to some other strategy that they could use.
Right.
Oh, so I wanted to add something else here. Candidates for absolute maximum and minimum. We're going to focus on the candidates for absolute maximum and minimum on a closed interval. We talked about what a closed interval was last time. So this turns out to be what the problems in the course are going to focus on. So we have okay, good. So let's say that we're focusing on the function over this interval.
Mm-hmm.
Okay, so where is the absolute minimum?
The absolute min is right there.
Okay, good.
And that's also a local minimum.
Excellent. That's right. It is. What does the tangent line look like at this point?
It is horizontal, so.
Excellent. So what can you say about the derivative at this point?
It's 0.
So doesn't that mean that, remember that our candidates for local max and min were critical points? Haven't we just proved then that those are also candidates for absolute maximum and minimum? Now we can see that the critical numbers are also candidates for absolute minimum and maximum because they also have horizontal tangents. So we can go back and fill that in over here. So we have here that one type of candidate here is, again, the critical numbers. What's the definition of a critical number?
A critical number is a point in the function where the derivative is either 0 or undefined.
So just like those could be candidates for local max and minimum, they can also be candidates for absolute max or minimum. On the other hand, do you see why I keep saying candidates? Is a critical number guaranteed to be an absolute maximum or minimum? Well,
Nope.
notice, is this point a critical point?
It is.
Yeah, but is it an absolute max or minimum?
It's not.
No. So the critical numbers are only candidates. You still have to check to see whether they're maximums or minimums. Okay, very good. Now, where is the absolute maximum on this function?
The absolute maximum is the right endpoint of the far end of the domain of the function.
That's right. Now, is this a critical point?
It's not.
Yeah. Actually, that's a little bit. Yeah, it depends a little bit on your definition. But anyway, we can clearly see here, would the tangent line here be horizontal?
No.
No. So it's not a critical point like these are here. Okay. So notice it's not enough just to find the critical numbers. It's not enough just to look for the points where the slope, where the tangent line has a slope of 0. What are the other candidates for absolute maximum or minimum? An absolute maximum or minimum could be at the critical point, but where else could it be? Where else do we have to check?
You have to check the endpoints.
That's it. Yeah, we have to check the endpoints. We just saw here you could have an absolute maximum or minimum at an endpoint, even though it's not a critical point. That's the difference between this and the local maximum and minimum. So candidates for absolute maximum and minimum. So the candidates could be critical numbers and candidates are critical numbers and the left and right endpoints. All right, so that's a new kind of theorem that we have here. And we're not going to prove this technically, but we've kind of proven it with our little drawing that it's reasonable. We did a drawing that demonstrated that these really are the reasonable candidates for the absolute maximum and minimum. Notice the new thing here is the local minimums and maximums, you didn't have to check the endpoints. For local min and max, if you use the definition your book uses, you don't have to check the endpoints, but you do for absolute minimum and maximum. Now, are the endpoints guaranteed to be absolute maximums or minimums?
No.
After all, this left point here is not an absolute maximum or minimum. So again, these are only candidates. We still have to check them to see whether they are, whether they really satisfy that or not. Okay, so now that's what we're going to be doing, checking those points. So we'll go on. And this is what your textbook calls the closed interval method, because these ideas work only for a closed interval. This is when you're trying to find the absolute maximum or minimum on a closed interval. Okay, as in the example that I had drawn a moment ago. 1 second. Okay, so, all right, you have that written down?
Mm-hmm.
Okay, so let's talk about how to attack this. So first thing we're going to do is we're going to be using a graphical approach here. So we could label our endpoints like so. I'll use the brackets to show that this is a closed interval. Now we need to check the candidates for absolute maximum and minimum. Well, we already know that one candidate here is x equals -1/2, because remember we have to check the endpoints. And we already know that another candidate here is x equals 4, because we have to check the endpoints. So remember, the other candidates are the critical numbers. So now we can proceed and try to find the critical numbers. Well, the first step for that is to say f prime of x equals, what would be f prime of x here?
3x squared minus 6x.
That's right. Good. And next, to find the critical numbers, we have to remember that by definition, a critical number is where the derivative is 0. Actually, remember, there's something else to check. Remember that the critical number could also be where the derivative is undefined.
Mm-hmm.
But can this function ever be undefined?
It can't be, because there's no Sorry, there's no denominator. I apologize.
That's okay. That's okay. That's the right answer. Good. Yes. So there's no fraction, basically. So we can't be dividing by 0. In your class, that's the only situation where functions are going to be undefined. Okay, so we don't need to worry about that. But eventually that will come up. So it's good to keep looking for that. So now we know f prime of c would be 3c squared minus 6c. Okay, and I'll stay on my screen, but you can talk me through how would you solve this equation.
Okay. Let's see. I would factor out 3c. And then I would have c minus 2.
Excellent. Now we should probably check to make sure we factored correctly. How can you see that you factored correctly?
We can distribute 3c. So 3c times c is 3c squared.
Good.
And then 3c times 2 is 6c. And that matches up with what we have above.
Yeah. Okay, very good. And then we would solve this, and we would get, what's the equation we get for the left term?
That would be, sorry, it's just going to be 3c equals 0. And the right is c minus 2 equals 0.
Because the only way that a product can be 0 is if one of the two terms is 0. Okay, very good. So these are the two critical numbers. Now remember, why were we considering these? We wanted these as candidates for absolute maximums and minimums. So now we can say some more candidates over here are x equals 0 and x equals 2. I'll go back to calling them x now because they are x coordinates, even though we found them by looking for the critical numbers. Maybe I should label that what I'm doing here is finding the candidates for the absolute maximum and minimum. All right, and there's no more candidates that have to be considered because of the theorem we talked about before, absolute maximums and minimums on a closed interval have to fall into one of these two categories, and we've checked both of those. But now, how can we tell? How can we tell which of these is the minimum, which of these is the maximum, and which is neither?
Well,
we know for sure one of them is the biggest on the function, and we know for sure one of these is the smallest on the function. How can we figure out which of these gives us the biggest value on the function and which gives us the smaller value on the smallest value on the function? Any ideas?
Yep. We can plug those values into the function, and if, for instance, 4 gives us the highest output, then that would be the absolute maximum.
Very good. Excellent. It's simple once you see it, so that's good. Excellent. Now, which function are we plugging these into? F or f prime?
F.
Very good. That's very important not to get confused about, though, because when they asked us to find the maximum and minimum values of the function, which function was the question talking about? F or f prime?
F.
Yeah. So if we want to know which of these is maximum in the function, we have to go back to f. That's one of the confusing things in calculus. People oftentimes don't know when do you use f and when do you use f prime. Well, as you correctly said, now's the time to go back and use f. That might seem a little weird because we haven't done that in this chapter, but now we're going to do that. Okay, so then maybe we'll start with an easy one. So what would be f of 0?
F of 0 is 1.
I can do that without my calculator.
Okay.
All right, and then if you want, you can use your calculator or by hand work out what f of 2 is.
8 minus 12, negative 4 plus 1, negative 3.
I'm using my calculator. All right, very good. All right, then we have to do f of 4.
I'll use my calculator. 4. 16 times 3, 48. 16, 17.
F of negative 1/2.
Point 125. 0.125.
Good. It's perfectly okay to say 0.125. That's right, too. Okay, very good. Okay, then what?
Now we see the absolute max is at x equals 4. So the point of the absolute max is 417.
Good. Good.
And then our absolute minimum would be, that's 2, negative 3.
Excellent. Good. That's very good. So what is the answer to the question?
Find the absolute maximum and minimum values of the function. The absolute max is 4,17. Oh, find the absolute minimum values of the function. Oh, okay, of the function. Okay, the absolute min is negative 3, and the absolute max is 17.
Very good. Great. So, for example, suppose that this is the profit function. This tells us that the best this firm can do is make $17 or $17 million, depending on your units of profit. Mm-hmm. And that the worst that the company can do, if it's run by an incompetent, is that they could lose $3 or $3 million. Okay, good. So technically, when they ask you for the absolute maximum and minimum values of the function, are they asking for inputs or outputs?
They're asking for the output.
That's right. But, you know, I'm pretty sure you would get full credit if you said the maximum was 417 and the minimum was 2, negative 3. Probably your grader's not going to be picky about that. So technically, the answers are 17 and negative 3. But it would be fine to say 417 and 2, negative 3 as well. That actually gives more information. Okay, good. One more thing I want to do just, to build up our intuition here is we can graph these points. So for example, here we have negative 1/2 and 0.0125. So that would be here, and then maybe around here, very close to the axis. Mm-hmm. And then we have 417. I probably can't draw that to scale and have it fit in here, but that would be very high up, like over here. Then we have 0, 1. It's not going to be to scale, but that would be somewhere like this. And then 2, negative 3. And then we can clearly see that this really is the absolute min, lower than all the other points, and this really is the absolute max, higher than all the other points. We know that none of the other points we haven't graphed can be higher because these were the only candidates. Okay, very good. And now would be a good time to confirm this by bringing out our calculator.
So y equals x cubed minus 3x squared plus 1. And I'm going to trace to x equals 4.
Okay, good. Before you do that, or you can do that trace, that's fine. So we can go trace x4. And that's actually, it looks like it's off the screen. right? So maybe we'll have to, but you can already see from the hash marks that it really is the maximum, right? Because each of these hash marks is 1. Here's 1, here's 2, here's 3. You can see that 4 is going to be the maximum on the interval. Also, you could see that if you could go to 5, that would be even higher. And if you could go to 6, that would be even higher, probably, but that's the end of the interval. So we can already see that 4 is going to be the maximum. And then how about our minimum at 2, negative 3? So we can trace to 2. And you can see here's the flashing cursor right here on this minimum. And you could see that if you could go further out to the left, you could eventually get lower than that. But you'd have to go past 1 to get lower than that. So that's not going to work. Okay, does that make sense?
Yeah.
Boy, well, you don't have to do this every time, but I can't resist. We could change our window here. The minimum x that we care about on this problem was negative 1/2. If you hit the window button.
Right.
So then you go negative 1/2 is x minimum. And our maximum x was 4, remember? So we go to 4 there. And then we can try hitting a graph for that.
I think we need to change the y value too.
So that it'll fit? Let's see.
Yeah.
Actually, I think it changed the y automatically for us.
Okay.
That's neat. Did it change the y? Or I don't know. Maybe it didn't change the y or not. Maybe it didn't. So yeah, it doesn't go up to 17 yet, does it? So, yeah, you're right. So, well, now I could just zoom out. From the middle.
Okay, cool.
And then we could go trace. Wait, oh, that zooming thing didn't work because then it changed the x again. All right, you were right. We should have changed the y. So my x minimum here, you don't have to do this every time, but it's interesting to do it this one time. So we've got the negative 0.5 is the x min, and then 4 is the x max. And you're right, we can use our advanced knowledge here that we're going to go down for an x min. Let's go down to, say, about negative 4. That'll give us room for everything. And we can go up to, say, about 20 for the y max. That'll give us room for everything. And now we can try graphing that. And that gives us a nice, beautiful picture that clearly shows that the absolute minimum here is at 2, this point here. And that confirms that the absolute maximum is at the endpoint blinking up here. Okay, so that wouldn't be a bad thing to do on the test. Basically, notice you can basically check all your answers on the test. You can check whether there really are maximums and minimums by actually drawing the graph and seeing whether they're actually maximums or minimums. We don't really have to guess. Okay, so the trick we used here is that you can change the x min and the x max to your 2 endpoints. And once you already know what your y values are going to range between, you can change those over here too. This is an alternative to using the zoom. This can be more accurate than using the zoom. Okay, and now how could we get these back to the standard values?
Well, I think when we graph a new function, it'll just reset them to.
Actually, it won't do that. It'll keep them like this. To get these back, we have to go back to zoom standard.
Okay.
If you zoom standard, then they'll basically what the zoom does is it changes your window values for you. So if we go back to zoom standard, that would change those back to what they were before. Okay, so anyway, we might do that in a couple more problems so we can get that technique down. All right, so that's how to do this type of problem. And the way I tried to write this on my screen in an organized fashion that would be good for you to imitate. This is the kind of way I would recommend doing these types of problems. Write down your list of candidates in an organized fashion in one place. You can test them all out in an organized fashion, and it's a good idea for our first few problems at least to draw a graph that illustrates them as well, so we're building some knowledge of what we're doing here. Okay, very good. Does that make sense?
Yep.
Okay, great. So, Okay, all right, I think this will work. So let's copy this down, and then you can try working it out on your screen, and you can try using the kind of organized approach that we did in the last problem.
Okay. Okay, so now we plug 0 into the function. Zero times 0 to 0 plus 0.
Great. Maybe a slightly better notation is to write f of 0 equals 0.
Okay.
But that wouldn't be the notation for this line.
Right, yeah. Okay. 36 times negative 72 plus 48. Negative 24. Okay. Negative 72. Four, negative 8, plus 16. Okay, so okay.
Okay, excellent. Let's graph those points. Let's graph all of our candidate points.
Okay. All right, so points. Negative 24 to negative 24 to 8.
And you can just get it roughly to scale. We don't have to be perfect. We just want to get a general feel.
Should I just go by fives instead of 24?
We just want to get a really general feel here.
Okay.
So yeah, so you could go by fives. That's fine with me. Now, we're not going to use the same scale on the horizontal as on the vertical. The vertical has to go between negative and positive 30. Mm-hmm. But the horizontal axis, those could probably just, each of those hash marks can just represent 1.
Okay.
Do you see why? Because the x values that we're dealing with are smaller than the y values. We don't need the same scale on the two axes. You should label those on the left as negative numbers. And the 30 at the bottom is negative 30. Okay?
Okay. So absolute max at 2, 5, something like that.
Oh, you ended up... Oh, okay. No, that's fine. Good. Good. That's good.
And then... 6, negative 24. So something like this.
Great.
And then 0, 0. And then what was that? Oh, 2, 8. No, 2, 8. 2, 8, 6, negative 24. 0, 0. Oh, that's it. Okay.
So let's label the absolute maximum and minimum. Okay, excellent. Good. Now I just realized there was something else I needed to do on my screen. So let's move back to my screen. There's something else that we should have done on this previous problem. So if you remember, this is the problem that we did before. Let's not just draw these points. Now I'm going to sketch the curve. I'm now going to sketch the curve here. So you might take a second to reorient yourself here. Remember that this was the left boundary. Now, is the function here? So the basic idea here is that the function has to be going up, and we know that it has a slope of 0 here, and we know it has to turn around here to get down to the minimum.
Right.
And we know it has to turn around at the minimum, so it can really hustle its way up to the maximum up here. It's got a long way to go. There we go. So notice we can actually sketch the whole curve. Now, obviously, this is not a perfect sketch. It's just an approximation. But this gives us the general idea here of what this curve looks like. So yeah, I really meant to be doing this because this is our ultimate goal here anyway. The main section of the chapter that your instructor said they were going to test you on is using these derivatives as an aid to graphing the function, right? The main questions here are going to be about using the derivatives as an aid to graphing the function. So that's something we should be doing here. Again, this is not a perfect, we don't know for sure that the graph looks exactly like this, but it has to have this general shape in order to go through these points. And something else we could have done then now is we can now confirm that we got the right general shape from our calculator, right? We can see in the calculator that we pretty much nailed it here. I guess we kind of cheated because in this one we did the calculator first, but I wasn't relying on my memory. I had forgotten what it looked like, and now we can see that they kind of match up. Okay, so now that I've shown you how to do that here, let's do that on the new problem that I just assigned you. Try to sketch the general outline of what the function must look like.
All
Because
right.
ultimately, that's the type of problem that we're trying to learn how to do, how to use these information as an aid to graphing the function.
So this is going up, and then it's going down. And it's coming back down. Ah. Something like that.
Something like that. Great. And now you can check on your calculator.
Okay. That's the derivative. I get 2x squared plus 8x. Okay. Alright, so yep, it looks like that. And then if I trace over to 2, it should put me at the max. Yep. And then at 6, let's see. Yeah, 6 you can't see right now, but if we could change it.
So let's use that. Let's go to our window. Actually, it'll be pretty helpful here, I think, to do that. So let's go to the window menu.
Okay. So I'm going to change y-min to negative 30. And go back to graph. Oh, error window range. Okay.
Well, what should be our x values? What should be x min?
X min should be 0.
Right. And x max?
6.
X max should be 6. Good. Y min should be around negative 30. And y max should be maybe about what?
10.
So give yourself a little leeway there. Good. And that should give us a nice picture.
Oh, cool. So trace over to 6. And it's the endpoint of the domain.
And you can clearly see it's the lowest point on the graph. And then what was supposed to be our maximum x?
X is 2.
So we can trace over to 2. Did you give that a shot?
Yep.
All right, and if you can see that, you can see the blinking cursor is at the maximum now.
Mm-hmm.
All right, so and it looks like. So can you scroll up your graph a little bit so we can compare it to the calculator? Good. All right, and you can see it's a pretty perfect match. So the point is that by using the calculus, we really were able to get a fairly perfect match to what the graph looks like. All right, so that actually would be a good exercise for us to go through here, because ultimately that's what these questions are about, learning how to graph the function. Okay, excellent. All right, well, that was a very good process. So I'll go back to my screen. Okay, here's another problem that another function to try the same exercise. Find the absolute maximum and minimum values.
All right. Okay. X squared equals 1.
Good. So now we're using some of those algebra ideas we went over earlier. Good.
Okay, so fourth potential. Plug these in. 0, 3, 9. So 0, we get 1. 3, we get 27 minus 9. 18 plus 1, 19. 1 minus 3, negative 2 plus 1, negative 1. Times negative 1 is 1 times negative 1 minus negative 1 plus 3, 2, 3. And double check. Alright, so we have those potentials, which means absolute max equals 319. Okay, I'm going to graph this. Alright, so we need to go to 20. So
Notice that on the y-axis, we don't have to go that high.
on the
y-axis is only going to go up to 3. There's nothing wrong with drawing it higher. But notice your biggest y, or was I, oh no, I guess the negative y-axis didn't have to go so low.
Oh, okay.
For example, you could have saved space by not drawing, you don't need to draw the graph symmetrically. The negative y-axis doesn't have to be as long if you're trying to like save space or something. There's nothing wrong with the way you did it. Maybe it's more intuitive that way. Okay, anyway, I shouldn't be, yeah, that's fine. You're doing good. So then what?
Okay, so, yeah, I see what you're saying though, but I'll just continue with this one.
Okay.
So, 19, and then x, we're just going from, x is not much. 1, 2, 3, 4. Second, 20, negative 20. Okay, absolute max is at max is at 319. So 1, negative 1. Okay. And then negative 1, 3. So like here. And 0, 1. Somewhere like this. Okay, so
let's label the absolute min and max. So what's the answer to the question?
The question was find the absolute max and min values of the function. The absolute max value of the function is 19, and the absolute minimum value of the function is -1.
Good. Now, what were our candidates or potentials?
We had our two endpoints, and we had our two critical numbers.
Now, what were the endpoints?
Our endpoints were 0 and 3.
So let's put a left bracket at 0 on the x-axis. You might want to put it exactly at 0.
Okay.
Right on the axis. And then a right bracket at 3. Right on top of the 3. I'm sorry, were you saying something?
Oh, no. Oh, sorry.
So that shows us we kind of made a mistake. -1 is not a potential. Because it's not in the right range. Now, in this particular problem, that didn't lead us to get the wrong answer, but in another problem, it could have. We kind of got a little lucky here. Okay, so that's something to watch out for. So that was a new issue on this problem that didn't come up before. We don't care about all the critical numbers. We only care about the critical numbers that are in the right interval, right? We only care about the critical numbers that are in the right interval. It doesn't matter whether -1 gives us a minimum or a maximum because it's not in the right interval anyway. So your work that you did on the left-hand side where you said C is 1 or -1, that was correct. But then we should not have copied the -1 over to our potentials. Perhaps we should cross it out over on the potentials. Because it was not a potential because it's not in the right interval. On another problem, that could have led us to the wrong answer. Good. So it's perfectly okay to see that -1 was a critical number, but then we cross it out because it's not in the right interval. That's something we should have been checking before, but we hadn't been. So that's a new thing to watch out for in these problems. We have to make sure the critical numbers are in the right interval, or they couldn't possibly give us the answer we're looking for in the question.
Okay.
Okay, good. So now let's go ahead and try to guess the graph.
Okay. So this is our endpoint.
Good.
This is our endpoint. So we're going down. We're going up. Something like that.
Okay, excellent. And it's good that you didn't start the graph at -1. Now, of course, you could have drawn from -1, but that wouldn't be relevant for this particular problem because this problem confined the domain to 0 to 3. Very good. So maybe we should start putting those brackets in our graphs because otherwise it would be easy to forget this. It might be a good thing to put in the brackets because otherwise it might be easy to forget what the endpoints of the interval are. All right, so now let's try to confirm that on our calculator.
Okay. X cubed minus 3x plus 1. I think we need to change our window. Or actually, let's trace. Okay, so at x equals 3, we need to change our window. So change the x minimum to 0.
Good.
X maximum to 3.
So we can make the x min and max exactly match our endpoints.
Mm-hmm. And then for the y min, we can use -3. And the y max, we can use 20.
Here's where it helps to have kind of already done the calculus work ahead of time because otherwise it's hard to know what the values for the window should be.
Mm-hmm. Okay, so now we can plug in our x values. X equals 3, y equals 19, and it's the endpoint, also the absolute max. And then x equals 1, -1, the absolute minimum. Cool.
And we can compare, and we can see this basically looks like the graph that you drew. Not exactly, but it has the right general shape. Okay, very good. All right, so we did learn something important on this problem. We have to make sure that we have to throw out any critical numbers that aren't in the right domain. We have to keep checking for that. Also, let's stay on your screen for a second. one more thing we should be checking. Remember, there can also be critical numbers where the derivative is undefined. So point to your formula. Take your time.
Critical numbers
outside the domain, outside the interval.
Okay.
And point to the derivative. How do we know that that derivative is defined everywhere?
Because it's a polynomial and there's no denominator.
Yeah, no denominator. So in this course, we can be confident that that won't be undefined. Okay, good. All right, so I'll go back to my screen. All right, again, on this problem, we have to find the absolute minimum and maximum.
Okay. All right. Yeah, I made a mistake. Okay. 3 times 2 is negative 6x squared minus 6x minus 12. Set it to 0. We take out negative 6. So x squared.
Okay, yeah. The first number is positive 2, not negative 2, x cubed.
Okay.
We miscopied the problem.
Okay. 6x squared. So 6x squared. squared plus x minus 2x minus 2. Okay, cool. All right. Negative 2. So that's 4, negative 8, that's negative 16. And then I think this one would just be, yeah. So 2 times 7 minus 27 minus 36. Okay. I think that's that, but 2, 8, 16 minus 4, 12, 4 minus 2, 4, no, 2 times.
Any particular reason why you're not just plugging that into the calculator?
Yeah, I am now.
Okay, good.
Okay.
Especially on something this complicated. Even if you do, even if you did these in your head, you would still have to check them on the calculator because it's so easy to make arithmetic mistakes. So.
Okay. So 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 1. Okay, that's right. And then negative 1 times negative 1 cubed minus squared minus 12. Okay. So the answer is the absolute maximum of the function is 8, and the absolute minimum of the function is negative 19.
Good, good.
And so we can write that down. Oops. Absolute max is negative 1. 8. So min is 2. Okay. Now I'll graph.
Good.
Need to go down pretty far, but not up. Then, yeah.
Are you using a different scale on the top and the bottom?
Right.
Okay, I didn't mean to use a different scale. I just meant you don't have to draw the y-axis as long. We should use the same scale on both of them. But the y-axis only has to go up 2 or 3 hash marks.
Gotcha.
But we should try to keep roughly the same scale. We can have a different scale on the x-axis and the y-axis.
Okay. And then 1, 2, 3, 4, 5. Okay, so -1, 8 somewhere here. 2, -19 somewhere here. 3, -8 here. -2. -2, 3. Somewhere here. I was just checking to see if all my critical numbers were in my domain. So.
Good. That's very important to check. Maybe, remember, the best way to check that is put brackets around the domain. You can put those right on the axis, yeah.
Cool, yeah, we're good here, but...
That would be a good thing to do from the start because it's easy to forget that step. Did you get the right coordinates for the -2? You might have miscopied them from the previous page. Do you still have that other screen that you can look at?
Okay, I had -2, -2, -3. Okay, and then -1 and 8, 2 and -19, 3, -8. Okay.
Let's see. You had -2. Okay, yeah. So what was the y coordinate when x is -2?
The y coordinate is -3.
Good. I don't think that matched what you put on the other canvas.
Somewhere here. Okay, so -2, -3, -1, 8, 3, -8, and 2, -19. Okay, so now we can draw. Well, this is absolute max, and this is absolute min.
Good.
Okay, now this is going up, and it's going down.
Good. If this was a test question, you'd want to fix that -1 point because it's not really, it's actually turning after -1, if you see what I'm saying.
Right, okay.
Yeah, it's not actually drawn as the max. You have to have it actually turn around at the point. But I see what you're saying for right now. Okay, good. Good.
That's still not quite there, but...
Good enough.
Okay.
We need to try to make the points actually be turning at the actual max and min. Okay, very good.
Okay, and now I can graph that on my calculator.
Sure.
Sure, it's somewhere. It's the wrong function. Okay. 2x cubed minus 3x squared minus 12x plus 1. And I fix my window. Zoom standard.
On these problems, you may as well just go straight to the window because we're always going to know kind of what kind of window we want. to the
Okay,
window
so
option, I mean.
my x min is going to be -2. X max is 3. My y min is negative, I'll put -20. My y max will be 10. Graph. Yep, it looks something like that. So let me trace over to x equals 2. Yep, absolute min.
Good.
X equals -1. Absolute max, and just want to see 3. Yep, near the endpoint. Okay, cool.
Okay, good. By the way, one more thing. Notice how your calculator now has foreshortened the y-axis. Well, that's what you can do in your own pictures as well. You don't need your y-axis to go as high as the negative y-axis. And also notice how your positive x-axis goes out to 3, but your negative x-axis is not as long. You can start kind of imitating that in your own pictures as just a way of managing your space. Does that make sense?
Mm-hmm.
Yeah.
Yep.
Okay, good. Well, that was a good method for that problem. The key thing is to remember to make sure to check that the points are in the right domain. I'll go back to my screen. So let's try a problem from the website. So again, we want to find the absolute minimum and maximum.
Okay. X³ minus 6x squared plus 9x plus 2. Okay. Okay. F of x. Okay. X squared negative 3x negative x x. Okay.
Okay, actually, I changed my mind. This was not the problem from the website.
Okay.
On the website, the range was -2 to 2.
Okay. All right. Calculator. Two cubed minus 6 2 cubed and squared plus 9 times 92 plus 2. Okay, guessing this is minimum. All right. So, 2 cubed times 6 times 2 squared plus Did I do something wrong?
No.
Okay.
I'm thinking whether I did something wrong, but you're doing good.
All right. 3 cubed minus 6 times 3 squared 9 times 2. It's 2. And 1 minus 6 is -5. Plus 9 is 4. Plus 2 is 6. That one. One minus 6 plus, yeah, that's right. Okay. So the absolute maximum of the function is 6, and the absolute minimum is -48. So our domain, good. Nope, bad. I should have seen that. Okay.
I kind of faked you out here by changing the domain in the middle. But anyway, it's important to check those points against the domain.
Mm-hmm. So those don't conflict there. Max and min, so that's good.
So it doesn't actually change our answer,
Right.
but it's still important to notice.
Okay. So we're going down very far, and then up. Okay. And we'll do tens. 10, 20, 30, 40, 50. It's our highest one. I know it's the same, but it's going to be 10. Okay. Well, okay, so 1, 6.
Good. So as you saw, you don't need to draw the y-axis as high on the positive side as the negative side. Good.
So 1, 6. We get 2, 48. 10, 20, 30, 40, 50. Somewhere here. Okay. And we also need our endpoints, which were, so this was good, this is good. We have one endpoint, okay. So 2, 4. Here. Okay.
Good. So one more thing, that we should be in the habit of putting in the brackets for the endpoints so that we don't forget those.
Okay. All right. Okay. So we're going up and down.
Good.
Okay, I think that's good.
Good.
Graph.
Sure.
Y equals x cubed minus 6x squared plus 9 plus 2. Go to window. Change my x min to, well, it's still negative 2. X max is still 3. Y.
Now, actually, the range. What was? Do you know what the range was on this problem?
Oh, that's right. Negative 2 to 2.
Yeah, I should call that the domain. The domain is negative 2 to 2. Good.
And then y min, I'll put negative 50. Y max, I'll put 10. And yeah, I guess my concavity is a little bit off, but
That's right. That's right. We didn't get the concavity right, but that's okay because we haven't started focusing on how to figure that out yet. Using the tools that we've talked about, we have a reasonable picture here that matches. That's good. You're right. When we move on to the concavity, we'll be able to get an even better match. But that's good for the time being. All right, and then we can trace out which 2 points.
oh, okay. We can trace out 1. Trace 1. That's 6, and that looks like the absolute max. And then trace negative 2, and that will be at the end point on the left, absolute minimum.
So there's a little blinking cursor there showing that that's our minimum. Okay, very good. That was a good process here. So again, the key thing is make sure that we've checked that all the points are in the right domain, but that was a good systematic process. Okay, so that was one of the problems from the website, so it looks like we understood how to get that right. I'll go back to my screen. Okay, let's try this problem.
X squared 2x squared plus 3. 2, 3. Okay. Okay. So well, I guess let's do this.
Dividing both sides by 4. Good.
And then can do 0, -1, and 1 fall within our 0, -1, and 1 fall within our domain of the function.
That's why that's good that you checked that.
So now we can put 0, -1, this one. So 2, 3, 0. So -2 to the fourth minus 3 times -2 squared is 3. Three to the fourth minus 2 times 3 to the second plus 3. Zero minus 0 plus 3. -1 to the fourth minus 2 times -1 squared plus 3. 0. And one more.
Okay, there's a calculator issue here. When you raise a negative number to an exponent on your calculator, you have to put the negative number in parentheses.
Mm-hmm.
Are you doing that?
Yeah, I think I did. Oh, not on the first term. Okay. Okay, gotcha. Yeah, I had that issue the other day, and I was dumbfounded for about 5 minutes.
Okay, good. Yeah. All right. So yeah, so it's good that you picked up on that. So then now we just have to be consistent about that. That's kind of that's a surprising quirk to me about calculators. That's one place I wouldn't expect to have to put in a negative number. But yeah, we need, when you raise a negative number to an exponent, we have to put in those parentheses.
Okay. So I get -1 to the fourth minus -2 times -1 squared plus 3, and now I get 2.
So I think we need to recheck the x equals -2 as well.
Okay. 2 to the fourth minus 2 times negative 2 squared plus 3. Okay. $11, and then 1 minus 2 plus 3, negative 1 plus 3, 2. Okay, so we have some symmetry going on here, I think. So we have 2 absolute, okay, so the absolute min of the function is 2, and that minimum is at x equals negative 1 and at x equals 1, and then the absolute maximum is 66 at x equals 3.
That's a very good way to describe it. Yeah, that was a good, accurate, careful way to describe it. So as you're working out here, it's possible for more than one point to represent the absolute maximum, and it's possible for more than one point to represent the absolute minimum. Good? Because when we defined the absolute maximum in our previous session, we said that it was greater than or equal to any of the other points.
Okay, so we got that. That is this point. That is that point and that point. We also have 0, 3, and negative 2, 11.
Good. A little point about notation here, though. I notice you're using the union notation there for your absolute minimum. That note, you might have seen that notation in class. That notation applies when you are combining two intervals. But those are not intervals, they're points. Gotcha. So it would be better just to say negative 1, 2, and, just write out the word and, 1, 2. That union notation is when we're dealing with intervals. I can see how you might do that because those parentheses are used for open intervals sometimes. But here the parentheses don't mean intervals, they mean points.
I'm trying to keep the graph on the same screen because I know it's a lot easier.
That's a good idea.
I'll get better at that. Okay, so
you could basically scroll everything to the left here. Well, it doesn't matter, I guess, because you don't have any more space on the canvas. That's fine. So where you are is fine.
Okay, so we're going up real far, up really high. And we're not going, okay, this is convenient, I guess. So we can just do this.
Good, that's a good idea. We don't need the negative axis, y-axis.
5, 10, 15, 20, 10, 20, 30, 40, 50, 60, 70. And okay, so start plotting negative 2, 11, somewhere here. Right, nope. Negative 2, 11, somewhere here.
Good.
366, somewhere here. Okay, 0, 3. Negative 1, 2.
The scale for this graph is wacky. That's okay. That's the best you can do. Good.
1, 2. Okay. Okay, cool. All right, so we got our 5 points. And this is the absolute max. And I'll leave that out for now until I draw it. Okay. So we're going down.
Good.
Well, absolute.
So this graph has a somewhat more interesting shape than the ones we saw before
Mm-hmm.
because it has the biggest power that we've seen before. This is the first problem with an x to the fourth. The higher the power is generally the more interesting the shape. And you can see there really are two minimums. Good.
Turn, 2 turns, 3 turns. Okay. Okay.
Good.
I can graph it on my calculator. Y equals, let's find the function. X to the fourth minus 2x squared plus 3. I'll go to my window. I make x min is negative 2, x max is 3, y min is 0, y max will make 70. I'll graph that. Yep, it looks like that. And I'll trace over to negative 1. And it's a little murky, but yeah, that's correct. And then 1, same thing. And then at 3, should get the endpoint. Yep.
Good. Because the scale here is so weird, it's hard to see that what's happening at the bottom and also see the maximum. But you can basically see here that that the graph does basically match the picture that you drew with the little hump in the middle and then increasing a lot off to the side. So good. So notice that even though this is a pretty complicated equation with an x to the fourth and a pretty complicated graph, but now using those calculus tools, we were able to get a pretty accurate feel for the shape of the graph, as we just confirmed on the calculator. Good. All right, I'm going to write another problem down on my screen.
Okay.
So now let's try to make things a little bit more interesting. Slightly different type of function. Oh, actually, there was one other thing I wanted to mention on that previous problem. Okay. So one other thing on that previous problem, there was a point in that problem when you were solving for the critical number. So you did a good job on the algebra there. This is you can see we're practicing the algebra we went over earlier. So there was a point when you got to this equation, and then what you did is you factored the x squared minus 1, right? Mm-hmm. But instead, we could just say that we know this has to equal 0, or this has to equal 0. Mm-hmm. And then if x squared minus 1 equals 0, what would you do then?
We would bring the 1 over to the right-hand side, and we have x squared equals 1, and then we take the square root of both sides, and we have x equals 1 or negative 1. So yeah.
Okay. The way you did it wasn't wrong, but I think it's there are some problems where this way will be better in this chapter. So it's good to point this out, that this is an alternative approach. There are some problems where that factoring approach could be a little confusing to you, and this one might be better. So I wanted to point that out. Okay. Good. So now I'll go back to writing down a new equation. So here's our next problem. Okay. So this is a little bit different than before. We'll have to adapt a little bit. So again, we're trying to find the absolute maximum and minimum on this interval.
All right. So okay, now we have potentials. X equals 0, x equals 2, and derivative. Okay, so we have to use quotient rule. Yeah, use quotient rule. So we get x squared plus 1 minus 2x times x over x squared plus 1 squared. Okay, is it legal to cross out this top term and then leave one of the two bottom terms? Like if I went this.
Well, before I answer, what's your guess? Do you guess that it's legal or not?
I think it is legal.
Okay. It turns out it's not legal.
Okay.
Good thing you checked. Yeah, maybe we'll talk about that more afterwards. So no, you're not allowed to do that.
Okay. All right. So let's see. I need to simplify a lot. X squared plus 1 minus 2x squared well, okay, I guess this is still not legal.
Right.
Okay. Well, what am I trying to do? I'm trying to define the derivative, a simplified derivative. So this is not simplified at all. I guess this is where me sucking at simplifying things is going to come back to hurt me. I don't know.
So actually, there is a simple way to simplify the numerator.
The numerator would just be... Okay, I see.
Okay, that's about as simple as we can make that derivative.
Okay. So now c equals 0. So
good.
Negative x squared plus 1, x squared plus 1 squared equals 0. Okay. Now we need to solve for x. And
good. I don't remember, maybe we haven't been doing this, but remember that you're actually, you wrote f prime of c equals
C.
0. So to be consistent, because what we're trying to do here is find the critical numbers.
Okay. So I guess I could multiply both sides by c squared plus 1 squared, and I would just have this. And then negative c squared equals negative 1, which is equivalent to c squared equals 1. I take the square roots. C equals 1 or negative 1.
Okay, so let's talk about that for a second now that we got this far. So now you can see we're finally starting to use some of that algebra, some more of the algebra we talked about at the beginning of the session. So that's good that you applied that correctly. So notice on this problem, remember you were worrying about how to simplify the derivative, right?
Mm-hmm.
But notice we didn't really have to simplify it at all in order to get this right. You didn't have to do any, you actually, if you'd wanted to, you could have left it as x squared plus 1 minus 2x times x over x squared plus 1 squared, because the problem is not about simplifying the derivative, it's about setting the derivative equal to 0 and solving the equation, right?
Right.
And notice how much simpler things happen. We certainly don't need to worry about simplifying the denominator, because the denominator is just going to disappear when we end up setting this equation equal to 0 and trying to solve it. And then, I guess the point is, it became much easier to simplify this once we set it equal to 0. So if you're not sure whether a simplification is legal or not, we may as well not do it in the first part of the problem, because our focus here is not simplification, but setting the equation equal to 0. And once we did that, things simplified. The denominator we were able to get rid of the denominator, and things became a lot easier to understand. Excuse me. Okay, good. So now we're on the right track. So let's continue.
Okay. Yeah, that makes sense. All right. Equals 1. X equals -1. Okay, so where's our function? There it is. Okay. You have 0 divided by anything is 0. And then 2 divided by 5. 1 divided by 2. And actually, this one's not in our domain, so not good. Okay, cool. So just have 3.
That's good that you noticed that. That was important. We would have ended up with the wrong answer otherwise. Good.
So our absolute max is 2/5. So at 2/5, our absolute min is at 0, 0, is 0 at 0, 0.
Good.
And we have one more point, and that's 1, 1/2. Okay, so now I'm going to graph this. Okay, so we need a pretty small scale. We'll use, there's nothing negative, and there's nothing negative x values. So we can do 1/5, 2/5, well, maybe by tenths. 1/10, 2/10, 3, 4, 5, 6, 7.
That's a good idea.
One 10, 2, 3, 4, 5, 5, 10, 6, 7, 8, 9, 10, 1. And 1, 2. Okay, so now we have 0, 0. Absolute min. We have 2, 2/5. So that's 4/10, 3, 4. Absolute max. And we have 1, 5/10. Oh, okay, that's not the absolute max. Okay. Okay. So 1, 5/10.
Okay, great. Notice I didn't have to tell you you made a mistake, you can see the value of graphing the problem. It forces you to see whether your answer is working or not. So this is a good example of how it can be useful to draw a graph. Some of the problems on the test will ask you to draw a graph, but even if it doesn't, it might be a useful check to draw the graphs because that saved us from that mistake that we were making. Okay, good. That's good that we caught that mistake. Good.
So we're going up. Oh. Going up. So max, absolute, min. Okay, now I'm going to graph the function, which was x over parentheses x squared plus 1. And zoom x min 0, x max 2, x min 0, x y max 1. So now trace over to 2. That should, trace 2 endpoint. Cool. Trace 1 absolute maximum at 5/10. And yep. Okay. Cool. We're good.
And what was the minimum?
The minimum is at 0.
And looks like the cursor is blinking there as well. Okay, good. So, by the way, notice this would have been your second chance to catch the mistake because when you graph it on the calculator, you'll be able to. At first, you thought the maximum was going to be at the endpoint, but if you put this on the calculator, you can see clearly that the endpoint is not going to be the endpoint is not the maximum. So that's a good reason to check these on the calculator as well to make sure that we're getting that right. Okay, very good. So, all right, so we'd been kind of on a roll on most of those problems. You were getting them all right without any mistakes, but there still are a few issues that we had to go over on this problem. So let's see, what were some of the issues here? One thing is, one thing that'll probably save you some grief on these is use decimals instead of fractions on these problems. Okay. Because what happened was it's hard to compare 2/5 and 1/2, right? But it would be easier to compare them as decimals. Although, let me ask you a question. Which would you rather have? Half a pizza or 2/5 of a pizza?
Half.
Yeah, if you have a big appetite anyway. So half is bigger. But we're less likely to make a mistake if we're using decimals. Let's do that now. How would you convert 2/5 and 1/2 into decimals when you're ready?
1/2 is 0.5 and 2/5 is 0.4.
Excellent. If you were going to check that on the calculator, how would you check it on the calculator?
1 divided by 2.
Okay, just wanted to make sure you knew to do that. Because notice it's easier we're less likely to make careless mistakes with the decimals than with the fractions. And then your scale could have been 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 on your graph. It's a little bit easier to think that through. Okay, so even if you get an answer in your head of 2/5, you can always use the calculator to put that into a decimal of 0.4. So that was an important issue on that problem. That's good that you caught your mistake, though. Everyone makes mistakes. The important thing is to recognize when we've made one of those. So let's go back to my screen now and talk about the algebra there a little bit. Or actually, let's stay on your screen for a moment. Let's go back and look at the algebra that you did with the critical number. Let's just kind of bask in that algebra so that we can see what was confusing us. So let's scroll up a little bit. So notice the key thing is you don't need to worry too much about simplifying the derivative. I'm sorry, I meant scroll down.
Okay.
Notice that you were worried about how much you could simplify the derivative, but we didn't have to simplify too much because once we set the derivative equal to 0, we can get rid of the denominator. And then at that point, it becomes much easier to work with. Right. So I just wanted to remind you, the thing that was causing us uncertainty, I think, was that we had a big complicated fraction. But on these problems, that doesn't need to worry us very much because once we set the derivative equal to 0, we're going to be able to get rid of the denominator anyway. And then from that point on, you'll probably have a better intuition for what the algebra should be. Very good. All right, so now I'm going to go back to my screen. So are we allowed to cancel the a here? The answer is that the best way to do this type of canceling is to first factor and then cancel. So can we factor an a out of the two terms on top?
We can. Oh, no, sorry. No, we cannot.
But if we can't, then we can't cancel.
Right. Okay.
So that's so it's important to have a method to tell whether we can cancel or not. So the key thing is you should only cancel when you can write things you should only cancel when you can write things like this kind of.
Okay.
This is the only time when it's safe to cancel, when you have two things the same like this. So if it's not clear whether you can cancel or not, you probably need to factor first. And what does it mean if you can't factor? If you can't factor, that means you can't cancel either. So can we cancel the a's here? Well, the best way to figure it out is to first see if we could factor out an a.
Right, which we can.
So what would go in the parentheses here?
1 plus b.
Good. And then what would be your next step to simplify?
We can cancel the a in the top with one of the a's in the bottom, so we'd have
That's
1,
right.
1 plus b over a.
Okay. So what I'm trying to do is give us kind of a method so we can figure out for ourselves when we can cancel and when we can't. If you can write the expression like this, then you can cancel. If it's not obvious whether you can cancel, you probably need to factor first, like we did here. And if you can't factor, then you can't cancel.
Okay.
All right, so that's a good way to tell. Remember, on this particular problem, if you're not sure whether you can cancel, you just might as well not do it, because the whole problem is going to be much simpler anyway once we set the derivative equal to 0. But in any case, this is the method for deciding when you can cancel and when you can't. Now, there is something else we have to consider on this problem. Let's see. So I forget, what did we get? So f of x equals x squared plus 1. You might need to go back to your screen and remind me, what did you get for f prime of x after you had simplified it?
After the simplification was negative x squared plus 1 over x squared plus 1 squared.
Let's stay on your screen for a moment and take a look at that. So let's see. Negative x squared plus 1 over x squared plus 1 squared. Negative x squared plus 1. Okay, good. So now let's go back to my screen. Now remember, our next step was we had to find the critical numbers. What's the definition of a critical number?
The critical number is the point on it's a point or points on the function where the derivative is 0 or undefined.
Good. Now you checked to see whether there were any points where the derivative was 0. Did you check whether there were any points where the derivative was undefined?
I did not.
So that would be a good thing to check here. So does it seem like there's maybe a possibility here that this derivative might be undefined some places?
Yeah.
Because there's a denominator, right?
Right.
That's the first time we've had that. So let me take you through this to show you how to do that here. By the way, so which denominator are we checking? X plus 1? Or which function are we checking for whether it's undefined? F of x or f prime of x?
F prime of x.
Yeah, we're not checking f of x because the critical number is where the derivative is undefined. We don't want to confuse those. Okay, so let me just give you a method for checking that here. We know we have to check that because there's a denominator. Well, what we can write here is we can say that we know that, let me clear this up a little bit. We could say f prime is undefined where, well, remember in your class, your instructor only has one type of situation where functions are undefined. In your class, functions are undefined when the denominator is 0, right? So in this case, f prime would be undefined if, oops, if x squared plus 1 squared equals 0. Do you see how I got that sentence? Okay. So this is the best way to systematically work this out. So next I'll write down f prime is undefined if, well, anyway, now we just have to solve this equation.
Right.
So go ahead and give that a shot. You can try that on paper or on your screen or whatever. Try solving that equation for x.
X squared.
And then we'll find what the x's are where it's undefined.
Okay.
Yeah, go ahead and do it on your screen, actually. We'll take our time with that.
1 squared. Okay, so
Okay, so let me interrupt you here. It looks like you're not actually, so this is a problem we can solve using the algebra we talked about earlier today.
Okay.
So it looks like you squared the x squared and the 1, but actually if you wanted to expand this, you would have to use FOIL.
okay, yeah.
And that would also, so what you did there is you wrote down the first and the last terms, but you didn't write down the inside and the outside terms, right? X squared plus 1 times x squared plus 1, you'd have to use FOIL. However, there's a better way. There's a better way. We talked about this a little bit at the beginning. How can you get rid of that square? We talked at the beginning, how can you get rid of a square in an equation? There you go.
Sorry.
That's okay. It's been a long session. We better wrap up. Good.
Long week. Okay. All right. So that's good. That's good. And we can't take a square. No. Yeah. No solution.
Okay. All right. So now we finally, I wanted to keep going until we got to see why we were going over that algebra at the start. So now we can see how some of that algebra comes into play here. So there's no solution to this equation. That would be a good point to review. So let's wrap this up on my screen. So what you figured out there basically, so I guess the way we would work this out is we could say, so do you see how I got to here?
Mm-hmm.
Now, what does it mean that this has no solutions? It means that f prime is never undefined.
Right. So, okay, yeah.
What we see here is f prime would be undefined if we could find an x squared that was equal to -1. But that's impossible. X squared can never equal -1. It's kind of a funny logic, but so f prime is never undefined. So are there any points where this derivative is undefined?
No.
No. So those, so we don't need to add anything to our earlier work. But we had to check this. We had to check this. It's not enough just to check that f prime, where f prime could be 0. You have to check, are there any points where f prime is undefined? So notice, even when there's a denominator, there might still not be any points where the denominator could be 0. Because this is because of the way this is set up, this is never going to be undefined. Notice, you can just see it from the start. Is there any way that we could ever get a 0 on the bottom of this denominator? Well, obviously not, right? Because we're starting with 1, and then we're adding another positive number to it. So we could just eyeball this and see that the denominator would never be 0. But this is the formal algebraic way to work it out. So you might want to study this after today's session. This, I think, is the best way to work out this part of the problem and to work out whether the function is going to be undefined or not. So we didn't make a mistake here when there was no solutions. That told us interesting information. It told us that f prime is never undefined. Okay, so that would be a good thing to review. A lot of the problems we did today, we were getting right, but we went over some harder stuff here at the end, and I have to just mention one other thing.
Mm-hmm.
Is this true or false?
That is false.
Yeah, that's what we were trying to do on that last problem.
Right.
Because if you were really going to square this, you would have to write it out, and then what's wrong with this? Well, this has the first terms and the last terms, but it doesn't have the outer and the inner terms. Mm-hmm. So basically, you can't distribute an exponent over addition. You can't distribute this exponent over addition. Instead, this would be the correct way to work it out. As we've seen, though, oftentimes you can get rid of the square by taking the square root of both sides. That would be legal. Okay, so a lot of these problems we went through very well. There was a few, but there were some important issues here at the end that we were dealing with, so that would be a good thing to review. Things started to get a little harder when the functions had fractions in them, right? So this problem that we just did would be a good one to review. Find the absolute maximum and minimum values of f on the given interval. So here's another problem. Let's try to attack this using the techniques we were talking about previously. You can try this on your screen. This is a problem from the website.
That's why. Okay. Question.
I think you miscopied or misinterpreted the problem. I think maybe my 4's look like y's to you. So that should be x squared minus 4, x squared plus 4. X plus 4, 2x, x squared, 2x, 2x cubed. 8x minus 2x cubed. Okay, thanks. So let's continue. Cool. Good.
Okay, so this cancels and this cancels. So we have 0 over okay, that's weird. So, wait. That means that this is just a straight line. Yeah. So we have 2. So the absolute max is 4 and the absolute min is -4. Well, you have to plug it into the function, but okay. So 16 minus 4 is 12 divided by 20. No, this is the same. So it's a horizontal one. I think. Sixteen by 4 is 12. 16 by 20. Okay. So there is no max or min. It's just a straight line, I think. Unless I'm doing this wrong. So graph. 1/5, 2/5, 3/5. Okay. Graph it up. Y equals x squared minus 4 divided by parentheses x squared minus 4 closed divided by x squared plus 4 closed. Nope, that's wrong. Okay. So we have some type of critical number at 0. Okay, so I guess that means x is that means this is a critical number. So, well, okay, yeah, I'm not sure how to prove that x equals 0. I mean that c or x equals 0. I'm not sure how to isolate a c here to make the equation c equals 0. So I guess as of now, I'm not sure how to complete the problem on paper.
Take a look to where it says f prime of x equal, well, actually, let's not even quite do that. So what does it mean if, what's one thing you should consider if the problem doesn't seem to be making sense?
That I made a mistake?
Yeah.
Okay. Something with derivative, I guess. Okay, x squared minus 4, derivative of the top times the bottom, minus derivative of the bottom times the top, 2x times x squared plus 4 is 2x x squared minus 4. So 2x times x squared is 2x cubed plus 8x minus 2x cubed minus 8x. 2x cubed minus 2 is 0. And 8x. Oh. Wait. Well, it changes anything. Yeah.
Okay, I'll give you some help. Where did you get the 2x cubed? So point to the 2x cubed, the first 2x cubed.
Where?
Oh, let's see how you wrote that, actually. Okay, yeah. How did you get that?
I multiplied this 2x by x squared.
Okay, fair enough. And then how'd you get the 8x?
I mean 2x by 4.
Okay. Then how'd you get the 2x cubed?
2x times x squared. X cubed.
And how'd you get the negative 8x?
2x times negative 4 is negative 8.
All right, so it sounds like what you're saying is that you haven't used that subtraction sign yet.
Right.
Okay, so yeah, so you really, does that subtraction sign refer to, that subtraction sign refers to both the 2x cubed and the negative 8x, right?
Mm.
Okay, so you really do need these parentheses.
Right, right. Okay, so I could rewrite this as all right. F of x, prime of x equals 2x cubed plus 8x minus 2x cubed plus 8x.
Okay, now if you're going to start by writing f prime of c equals 0, we may as well be consistent and keep using the c underneath that.
Okay. Okay. Negative 4 divided by 4, negative 1. Wait, sorry. Yeah. So 0, negative 1. Zero, negative 1. Okay. Okay, trace over to 0. Then we get y equals negative 1. And then trace negative 4. Good. Trace the 4. Good. Okay.
Okay,
Everything
what did you
looks
use
good
as
now.
your window settings here?
I didn't change them. I had a X-Men. Okay, I should change them. Negative 4 and 4. I can make my Y then I'll just go with 2, negative 2, I mean. And then y max I'll just make 1.
That makes sense. Good. That just gives you a little bit more of a close-up of the part of the graph we're looking at. It doesn't contradict anything that you'd said before. Okay.
Okay.
So let's see. So now I think we have the correct answer. So this was a problem from the website, so it looked like this would be fair game for the test. So there were some issues that came up here that we should talk about. Now, one thing is this kind of shows you the value of checking your answers on the graph. I think you were suspecting that the graph was really a horizontal line, right? But you can see from the calculator that turned out to be incorrect. So we must have been making a mistake somewhere along the way there. I guess I'll go back to my screen now.
Okay. Sorry, 1 second. Okay.
Actually, I'm just going to write something down on my screen, and now I'd like you to try it on your screen. So I got a minus b times c minus d. Try to work out how you might simplify this or re-express this on your screen.
Okay. Okay. A minus b, c minus d.
How could we re-express that or simplify it?
All right. It's wrong. All right. So
That's okay. Take your time.
let's see. A minus bc minus b plus bd. Oh. Plus bd. Okay.
Okay, good. So read the first term aloud to me. What's the first term in your new line?
A.
Excellent. I know where you got that from. You just copied it down from below. Good. Now, could you read aloud the second term?
Yeah. Negative bc.
Excellent. Good. So describe to me how you got that term.
We took a negative b and we multiplied it by a positive c.
Exactly. Yes, that's exactly right. And then how did you get, what's the third term in your second line?
bd.
Plus
Positive
bd.
bd.
Good. And how did you get that?
We took a, we got a positive bd by taking a negative b and multiplying it by a negative d.
Okay, that's right. Okay, so I'll go back to my screen. All right, so as we discussed last time, in many ways, the calculus is not the challenging part of some of the material we're going over here. What's going to be challenging is having to go back and review some of the algebra that we need for these problems. So that's the purpose of doing these, to try to find the algebra issues that are coming up. So that was what was giving us trouble in this case. So what you're doing here is you're using the distributive rule. We're going to multiply what's outside the parentheses by the terms inside the parentheses. So what is outside the parentheses that we're going to multiply times the things inside the parentheses?
Just b.
Now I would put it differently. What's outside is negative b.
Negative b.
That's the key. The key here is that we're not multiplying these by b. We're multiplying them by negative b. If you like, well, would you agree with this? Do you agree this is true? Or not?
Yep.
Yeah.
Yeah, that's true.
So if you like, you might have rewritten it like this to make it easier to see what you're doing. This just confirms we're multiplying by everything by negative b. We're not just multiplying by b, we're multiplying by negative b. I'm not saying you have to write it out this way, but this makes it clearer that we're multiplying by negative b, not positive b.
Okay.
as we go through here. Okay, so that's a common mistake that people have when they're using the distributive rule. Notice that when you use this approach, there's no need to really worry about parentheses in your answer. You should just say negative b times c is negative bc, negative b times negative d is positive bd. Notice there's no need to put in any parentheses here. So this is a little different from how we went through the problem the first time. It's a little different. You might want to change your notes. This is a superior way to do the problem. Instead of, so what we did when we did this together is we did something like this. We did this first, and then we did this. But that's actually not really the best approach. The best approach is to avoid the need for the parentheses in the first place by just multiplying everything by negative b, if that makes sense. Okay. Okay, so that's the way to apply the distributive rule there. Okay, well, try copying this and try this on your screen. Try simplifying this.
CD. Okay. Maybe. Okay. Okay.
Okay, good. The way that you were doing it before would have worked as well, but maybe it's an unnecessary complication. We can just go kind of straight to the answer, as long as we remember that when we're doing the distributive rule, we're not multiplying by CD. What are we multiplying by?
A negative CD.
Okay, as long as you remember that, then we can just go straight to the answer, just like we did here. Okay, so that's just some more algebra that's important for us to review. I'll go back to my screen. Can you think of any way to simplify this expression?
Well,
this expression. Is there any way to simplify this expression?
we could bring it to the top,
Bring who to the top?
the bottom.
I'm not quite sure what you mean by that.
We could rewrite it as 0 times close parentheses x cubed plus log of the natural log of x plus a square root of sine cubed x close parentheses to the negative, no, to the 1, I don't know.
Okay, actually,
no
you could have done. You almost you lost your convictions at the end, but yeah, you could have done that. You could have multiplied this by this thing on the bottom to the -1 power. That's true.
Mm-hmm.
Okay, but instead, I was going through for something simpler. Well, how about this? Can you see any way to simplify this?
No.
How about this? Can you see any way to simplify this?
Yeah, 3.
Great. How can you simplify this?
4.
How can you simplify this?
0.
That's right. That's a lot simpler, isn't it?
Mm-hmm.
How could you simplify this?
0
Yeah, what does 0 over 5 mean?
means 0.
Right. But well, what does 6 over 2 mean? It means 6 divided by 2.
Right.
So this means 0 divided by 5. Fractions mean division. How about this? Is there any way to simplify this?
0.
That's right. Is there any way to simplify this?
0.
Okay, so going back to this example, how could you simplify this complicated, scary-looking example?
0.
Yeah, it's just 0. Okay, so when there's a 0 in the numerator, we can always simplify that. Now, when you were doing this problem the first time, I think you ended up with, you had made a mistake in your algebra, and after the mistake in your algebra, you ended up with this. Now, this was a mistake. There shouldn't have been a 0 on the top, but given that we have that 0, we can simplify things some. How could we simplify this expression?
0.
So what you really figured out was that the derivative was 0 everywhere. So remember, there was a point here where you were trying to get this to work by trying to work out this, perhaps. But this didn't really make much sense because there's no point plugging in on the bottom here because anything divided into 0 is just 0. So that's just something that might have made it clearer that we'd made a mistake, perhaps, as we were going along. Okay, so that's something that's worth keeping in mind. You can always simplify when there's a 0 in the numerator. All right. That wasn't the most important thing on that problem, but I thought I'd mention that. What does it mean? So on this problem, f prime was not really 0. It just seemed like that because of a mistake. But let's say we're doing some other problem, a new problem, and on that problem, f prime is 0 everywhere. What does that tell you about the graph of the function?
It's a horizontal line.
Excellent, that's right. You didn't quite say that correctly before. When you were doing this before, oops, I didn't write this correctly. I meant to say, if f prime is always 0, that means we have a horizontal line. So it could look like this, or maybe it looks like this, or maybe it looks like this. Any of these would be possibilities. What you said before was that it was a straight line. But what you said here was better. It's not just straight, it's horizontal. And here's how you could see that you made a mistake on the previous problem, because your work was implying that it was a horizontal line, but when you graphed it on the calculator, you saw it was not a horizontal line. By the way, let's say that you had figured this out on a new problem. Let's say that the derivative is 5 for all x's everywhere. How would you interpret that graphically? What does that mean the graph looks like?
Let's see.
I'll give you some help.
I'm
sorry, you were saying?
Yeah.
So remember that the derivative is the slope. So this means that the slope is constant. Well, there's only one type of graph that has a constant slope. What type of figure has a constant slope? Only straight lines have a constant slope.
Right.
So if the derivative is a constant, that tells us that the graph must look like this. This is a straight line. That's why I said we shouldn't just say that this is a straight line. This is not just a straight line, it's a horizontal line. But here we have that this is a straight line. And I know it's upward sloping because this is a positive slope. And what's the slope of this straight line?
5.
Notice that in this case, the function and the tangent are the same. Here's the function.
Right.
Here's the function f of x. But if I drew its tangent, it would be right on top of it. The tangent to a line is just that same line. All right, so this is what it means when the derivative comes out to be a constant. If the derivative is a constant, then the graph is just a straight line. By the way, notice we're not talking now about what it means when the function is a constant. That would be a whole different issue. This is not what happens when the function is a constant. Here's the function. Notice the function here, would you agree the function here is not constant?
Correct.
Because it's increasing. But its slope is constant. Okay. So suppose you did a problem and you got that f prime of x was, say, 0.3 everywhere. How would you interpret, what does that tell you about the graph of f?
It's going to be a straight line.
Upward or downward sloping?
Upward.
Steep or shallow?
Shallow.
Because the slope is very low.
Mm-hmm.
So it would look maybe something like this. Okay, unfortunately we've been so caught up in the mechanics here, we haven't had as much time as would be nice to talk about what derivatives mean. So here's just a couple of simple examples of what some derivatives mean. So this is an example of where f prime of x is 0. These would be good examples to have in your notes and meditate on a little bit. This is an example where f prime of x is 0. This is an example where f prime of x is 5 everywhere. This is an example where f prime of x is 0.3 everywhere. I'll give you one more example. What does this tell you about the graph of f?
It's a straight line and the slope is decreasing. Pretty
Say that
steep.
last part one more time.
It's a straight, the function's a straight line,
Okay.
and the slope is decreasing.
Okay, that last part wasn't quite right. The slope is not decreasing, the slope is constant, right? You see why I would say that? This is the slope right here. It's -3 everywhere. I think what you were trying to say is that the function was decreasing.
Oh, okay, yeah.
Maybe that seems persnickety, but it's actually very important to not confuse those things. Basically, you were confusing the derivative with the function, and that's an important mistake to watch out for. This has a constant slope, which means it's a decreasing function. That might seem like a minor detail, but that's actually really important for understanding this material. I should probably draw that a little bit steeper. This has a constant slope, but what does it mean that the slope is negative? Negative slope means decreasing function. Okay, well, like I said, these would be good to go back and meditate on a little bit here. So notice, so these would be, so for example, in this case, is this a case where the slope is increasing? Is the slope increasing here?
No, slope's constant.
The slope is constant, the function is increasing. Good. Is this a case where the function is constant? Is the function constant here?
No, it's not.
The slope is constant,
Uh-huh.
which a constant positive number, so the function is increasing. Those are actually really important distinctions. Okay, so we'll move on now, but these 4 examples would be good to kind of write down and think about to get a little bit better sense of what derivatives mean. Now, these are just the derivatives for straight lines. This is what the derivative of a straight line means. Usually we have a much more complicated example like this. In this example, the slope is constantly changing. But at least here we can interpret what it means when the slope is constant. This is how we could have seen we were making a mistake on that last problem, because in the last problem you basically deduced that the derivative was 0 everywhere, which would have meant that the graph had to be a horizontal, not just straight, but a horizontal line. But you saw from your calculator that that wasn't right. And I think you saw that that wasn't making sense there. We were just having trouble finding the mistake in the algebra. Okay, so that last problem would be an important problem to go back and try again. That would be typical of what you might see on the test. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.